Welcome back, everyone, for the lectures from the afternoon of this first day of lectures in our workshop. Now, I'll have the pleasure of introducing Gabriel Dantas. He is a master's student in the Polytechnic Institute here at the University of São Paulo. He will present Exploring Artificial Intelligence for Simulating Short-Term Geological Models Using Operational Data, Challenges and Opportunities. I welcome you. Thank you very much for participating and giving a bit of what you've been doing at the university. Thank you.
Olá a todos, eu queria agradecer o convite. Para mim é muito importante estar participando de um evento como esse e poder estar compartilhando um pouco do meu conhecimento com vocês. Bem, o tema da minha apresentação vai ser explorando a inteligência artificial para atualização de modelos de curto prazo utilizando os dados operacionais e aí trazer algumas oportunidades e desafios referentes a esse assunto. Bem, eu dividi minha apresentação com uma breve introdução sobre inteligência artificial. Peguei um artigo de revisão literária sobre o uso da inteligência artificial no setor de exploração, operação e fechamento de mina. Trouxe dois cases para a gente discutir um pouquinho, trazer o conceito de circuito fechado de controle e automação sempre contínuo e os desafios de implementar isso na indústria. Bem, inteligência artificial é um assunto bem antigo. Desde 1959, acredita que foi desenvolvido o primeiro IA, que é o Game Checkers, desenvolvido por Arthur Summer, e ele define inteligência artificial como o machine learning como uma faceta da inteligência artificial que os sistemas são capazes de aprender sem ser explicitamente programados. Então vamos aí, pegando esse conceito de machine learning, que é algo que pode aprender com as informações, né? Eu peguei o artigo da Jung e o Sochoi, que eles fazem uma revisão do que foi publicado nos últimos 10 anos para dar um panorama de como a inteligência artificial, os algoritmos de machine learning estão sendo utilizados no setor hoje. Então, eles descobriram que eles identificaram 255 modelos, onde eles classificaram em 12 tipos. Existem modelos de vários tipos, né? Supervisionado, não supervisionado, sempre supervisionado, aprendizado por reforço, arco crítico. Existe uma série de modelos de machine learning diferentes e cada modelo vai ter sua aplicação em algum setor. E ele ele identificou 109 papers no trabalho dele e dividiu a área de atuação desses papers em 34 áreas, onde a gente vai focar aqui nessa parte aqui de exploração, onde ele coloca aqui a parte de prospecção mineral, modelamento, mapeamento e a parte de planejamento de lavra. Nessa pesquisa dele, ele engloba também os dados de operação de mina, onde que a maior parte dos artigos focam, e a parte de fechamento de mina, onde a gente não vai dar um foco hoje. Então, o que eles descobriram nessa pesquisa aqui? Desses 109 papers, 26% estão relacionados à exploração mineral. Onde, da exploração mineral, 38% desses papers, esses 11 aqui, são na parte de prospecção, modelamento e mapeamento. Então, mostrando a importância desse setor na parte de machine learning, que ele é algo que merece a nossa atenção. E ao longo desses últimos 10 anos que ele considerou, de 2011 até novembro de 2020, há um crescimento das publicações desse tema. Então, é um tema que está ganhando cada vez mais relevância, que vale a pena a gente investigar. Além disso, nessa revisão que eles fizeram, eles colocam em cada área quais são os modelos mais utilizados. Então, vamos aqui na parte de Mineral Exploration Targeting. Eles estão utilizando muito SVM, 10 artigos onde eles identificaram que está usando esse modelo, Ensemble Learning, Deep Learning. Então, quando a gente for estudar alguma coisa que queira utilizar Machine Learning, é muito importante a gente ver aonde esses algoritmos, esses modelos estão sendo utilizados para poder você fazer a escolha do modelo adequado para a situação que você está querendo utilizar machine learning. E aí eu vou trazer um dos cases que eu preparei, baseado no artigo da Camila da Silva, onde foi publicado na Natural Research em 2022, onde ela vai comparar dois métodos diferentes, um aplicando Elliptical Radial Basis Function Network, que é baseado em interpolação Elliptical Basis Function Interpolation, associado com redes neurais, e Support Vector Machine Regression. Então, ela, a partir dos furos de perfuração, faz análise química, obtém um teor, e a partir desses furos ele vai gerar os modelos preditos, né, pelo machine learning, e vai comparar os dois. Então, aqui à esquerda, eu tenho o modelo baseado em Elliptical Radial Basis Function Network, que ele mistura a interpolação radial com o modelo de redes neurais. E à direita aqui eu tenho os modelos de SVR, que é o Support Vector Regression. Então, a gente consegue ver que modelos de machine learning diferentes desempenham esses resultados diferentes. A gente consegue ver aqui os furos de sondagem marcados, ou com um teor aqui marcado de 0 e 1. E você consegue pegar aqui o furo 3 como o nosso principal exemplo, você vê fortes diferenças aqui entre um aprendizado e outro. Na minha concepção, isso daqui parece muito mais realista, tem um formato muito mais agradável. Isso daqui tem alguns hotspots, algo esquisito. Então, ela vai comparar algumas métricas de desempenho para comparar esses modelos. O que ela fez? Ela pegou, simulou com inverso da distância, triagem ordinária, o CVR com Intrinsic Collocated Concreting e esse método aqui que é o Elliptical Radial Basis Functions. Então, o que ela fez? Ela pegou, fez a simulação e calculou no modelo de blocos, classificou o que é minério e o que é estéreo. E comparou com o gabarito que ela tinha. O que ela obteve? Que a acurácia média para os 10 desmontes que ela estudou, o mais acurado foi o modelo de Elliptical Radial Basis Function, o Elliptical Radial Basis Function Network, e também foi o que menos errou, que menos classificou errado esses blocos. Porém, o método de SVR ficou muito próximo, mostrando que os modelos de machine são bem acurados aí para poder fazer essa parte, sendo até desempenho melhor do que a ordinária triagem, que é o mais utilizado hoje em dia na mineração. Bem, esse foi um exemplo que ela pega os dados, utiliza os modelos e o modelo dá um resultado. Porém, dá para ir além disso, dá para trazer esses modelos e torná-los recorrentes, utilizados na mineração com dado operacional em tempo real. É isso que está propondo o Amish Kumar e Russos de Mitrakopoulos. Russos de Mitrakopoulos, atenção nesse ano, quando vocês forem estudar Machine Learning, o Russos de Mitrakopoulos é um dos grandes pesquisadores desse tema. Ele é responsável pelo laboratório Cosmos, onde ele tem dado muitas contribuições muito relevantes nesse tema. Então, quem quiser pesquisar Machine Learning, recomendo ter muita atenção nesse cara aqui. Nesse paper, estão propondo um modelo de Machine Learning para atualizar automaticamente os modelos geológicos de curto prazo, baseados em dados de operação. Então, aqui ele tem a operação de mina, onde ele recebe Spatial Selection Data, que seria sensores alocados em equipamentos, que conseguem tirar análises químicas pontuais da mineradora, ou da mina, da cava, com a georreferenciado, e também pegar os dados temporais do sensor após o processamento mineral para pegar um teor na planta. E aí, utilizando esses dados que são gerados de forma recorrente, melhorar os modelos de machine learning e trazer modelos cada vez melhores, com um modelo cada vez mais capaz de aprender melhor a fazer essas simulações. E como ele vai fazer isso? Ele utiliza o Arco-Critical Agents Training em Process Learning Object. Eles estão usando o método de arco crítico com reforço, que baseia-se em você ter um algoritmo de reforço, onde ele sugere uma ação, que essa ação vai interagir com o ambiente vai dar uma observação para o o ambiente vai fornecer uma observação, o agente vai avaliar se essa observação atinge ou não a meta estabelecida para o aprendizado, que seria o policy, e aí vai atualizando os modelos com mais informação e o modelo vai ficando cada vez mais acurado ao longo das interações, onde ele vai recebendo cada vez mais dados. Então, você tem um ambiente, ele vai receber a ação a partir dos modelos iniciais, vai fazer o processamento aqui dentro do machine learning que ele propôs, ele vai entrar no estado de recompensa. Se ele acertar, o modelo é recompensado, falando, oh, você está acertando, continua desse jeito, ou se ele está errando, ele vai receber alguma correção a partir dos dados gerados ao longo do processo. Então, como isso vai ser feito, né? Então, você tem os dados temporais, que vão sair da planta de beneficiamento, os dados espaciais, que vai ser dos equipamentos que estão lá na cava, as simulações iniciais vão alimentar o modelo de AI, ele vai gerar novos modelos, esses modelos vão ser atualizados, são retornados para o modelo, e aí fica esse ciclo de autoalimentação, onde eles vão aprendendo cada vez mais e gerando modelos mais precisos. Então, né, vamos pegar os resultados dele aqui, vamos passar um pouquinho sobre o que está rolando. Então aqui ele vai pegar os furos de sondagem, ou furos de hole data, que seriam os furos de perfuração ali para fazer o modelo de curto prazo. E ele faz as primeiras simulações. Então esse aqui seria o resultado das primeiras simulações, utilizando a primeira rodada de simulação. E aí, após fazer a primeira rodada de simulação, ele vai receber os dados espaciais. Onde que ele representa aqui a coleta dos dados espaciais, B representa os dados com erro, e C representa a tomada dos dados após o processamento mineral, que seria um sensor que está alocado após a moagem, que está coletando o teor de cobre, nesse caso. E aí você tem a simulação inicial, o modelo atualizado, depois que vai receber esses dados, e aqui é o gabarito dele. Então você consegue ver que na primeira simulação, ele chega até aqui perto, mas não está tão próximo aqui. Então, conforme vai passando o tempo, ele vai recebendo esses dados, o modelo vai ficando mais acurado. Então, ele fez algumas simulações e chegou mais próximo da realidade a partir do modelo B aqui. E, além disso, ele checa o quão confiável é a informação gerada nos modelos. Então, ele vai pegar primeiro a simulação inicial, que provavelmente deve ter usado agregagem ordinária, onde vai fazer a primeira simulação com os dados de perfuração de curto prazo e vai observar a aderência aqui no histograma. E, além disso, vai verificar a aderência aqui no variograma. Então, você vê que a simulação inicial já está bem próximo, porém, quando ele adiciona os dados espaciais e os dados da perfuração, você vê uma maior aderência dos modelos simulados com os dados espaciais e os dados de perfuração. Com o variograma, acontece a mesma coisa. Você vê uma maior aderência entre os dados do data com a simulação. Ou seja, conforme você vai adicionando essas informações, o modelo vai aprendendo cada vez mais, ele se torna mais eficiente em fazer as predições dele. Além disso, esse modelo é capaz de prever o teor que vai sair na moagem. O que para mim é uma grande inovação, o que muda o planejamento de lavras. Você é capaz de saber o quanto vai dar o teor na planta a partir dos dados operacionais de perfuração, você consegue ter previsibilidade de produção. E isso pode mudar a função-benefício para você fazer o planejamento de lavra. Conforme o modelo vai aprendendo, vai conseguindo prever o resultado na planta, você ganha tempo para tomar ações corretivas e conseguir melhores resultados na tua operação. Isso que eu estou falando de conseguir ter essa previsibilidade, conseguir alcançar esse ciclo de controle, é um conceito proposto por Bendorf em 2015, onde que ele fala do ciclo de controle fechado, de automação e controle semi-contínuo. Que no lugar de você ter esse padrão que é utilizado hoje na mineração, que você tem exploração e coleta de dados, você vai fazer o modelo de recursos, reservas, fazer o planejamento de mina e as predições de teor, operacionalizar e fazer o processamento do beneficiamento mineral e a venda, e aí você faz uma comparação do que você produziu com o que você tinha nas reservas, fazendo um mining call factor. Você vai mudar esse esquema, você vai tornar ele cíclico. No lugar de você ter o estimado comparado com o medido, você vai ter o predito versus o medido. E uma informação de uma área vai sempre servir para alimentar outra, para conseguir você ter previsibilidade ao longo desse ciclo da operação, que é o conceito do Bender. E no meu mestrado é isso que eu estou tentando aplicar para a indústria do ouro. Porém, né, nos papers, tudo, tá lá os resultados bonitinhos, mas aplicar isso na indústria exige alguns desafios. Não é só chegar, ter um modelo e aplicar. Ele exige uma série de comprometimentos da indústria, dos funcionários, da equipe que vai trabalhar com isso, principalmente em relação à engenharia de dados. É muito importante, se você for fazer um trabalho que envolva machine learning, quer deixar ele operacionalizado, é que esses dados estejam disponíveis para o uso, o que é um dos grandes desafios hoje que eu vejo da mineração para ser superado, é ter os dados organizados, estruturados e consumíveis. Então, os dados eles têm uma fonte de geração, então você tem que identificar onde essas informações são geradas, como coletar, como ingerir para poder você armazená-las, realizar as transformações e tornar disponíveis essas informações para poder fazer as análises, dar informação para os algoritmos de machine learning e também os gêmeos digitais. Os gêmeos digitais são ambientes virtuais onde você consegue simular o que está rolando na operação a partir dos dados e você conseguir realizar essas predições. Além disso, da infraestrutura, você conseguir ter rastreabilidade da informação ao longo da operação para você saber com que você está alimentando a planta para poder registrar corretamente. Por exemplo, você associar aquela frente de lavra com o que rolou na operação para você conseguir fechar esse ciclo. Nesse caso aqui da mina que eu estou trabalhando hoje, o material sai da cava, ele tem vários destinos possíveis. O pátio home, o pátio de low grade, o pátio para estéreo e o pátio norte. E às vezes o planejado, às vezes não, quase sempre, o planejado é diferente do realizado. Então você ter um planejamento não quer dizer que o pessoal vai executar. Então é muito importante você utilizar os sistemas disponíveis para conseguir garantir a rastreabilidade da informação. Como a gente fez isso? A gente pegou informações dispersas em diferentes sistemas. Então, sistema de despacho, informações do modelo geológico, modelo de blocos, dados sólidos de liberação, onde a gente integrou tudo dentro de um sistema que a gente consegue associar a informação da viagem do caminhão com a qualidade do minério de acordo com o planejamento de lavra, para a gente conseguir fechar esse ciclo. A gente chegou a uma proposta lá de fechar esse ciclo, né, nessa empresa, mas a demanda deles era anterior a essa, era organizar as informações, conseguir ter essa rastreabilidade. Então aqui a gente consegue associar as viagens, a gente consegue não só as informações se é high grade, low grade, a gente consegue falar qual que é o teor, qual que é a litologia, de qual liberação veio e quais são os blocos ali presentes. Para poder realizar um plano de blendagem, que a gente consiga registrar o que está alimentando na planta, para poder ter essas informações e aplicar naquele sistema muito similar que o Kuhlmann fez junto com o Dmitry Akopoulos, e conseguir fazer modelo preditivo de como vai ser o teor após a alimentação com uma blendagem específica na saída do moinho. Além disso, outros desafios é o quê? Investimento. Exige tecnologia. Você não consegue fazer coleta de dados, armazenamento de dados sem investir em tecnologia. Hoje, operações mais antigas, existe muita resistência em colocar novos investimentos, equipamentos, sensores. Tem que capacitar as pessoas têm que estar abertas a receber esse tipo de tecnologia, a confiar nela. E a questão do mindset. Existe muita questão de insegurança em relação à inteligência artificial, em relação a roubar cargos, alguma competição em relação ao trabalho humano. Mas eu vejo que o machine learning não vai roubar o emprego de ninguém. Ele vai mudar a forma como você se relaciona com o trabalho. No lugar de você estar preocupado em realizar, ficar executando esses modelos repetitivamente, você vai se preocupar em coletar melhores informações, você vai ter um foco maior na operação, você vai estar lá acompanhando os processos para garantir uma melhor qualidade desses dados. Então, isso aqui são as minhas referências que eu usei para ajudar a apresentação. E, bem, para concluir, eu gostaria de agradecer a vocês pelo convite. E estou aqui aberto a dúvidas, sugestões e podemos conversar um pouco mais aí sobre esses cases. Obrigado. Acabei indo muito rápido. Um pouquinho, não tem problema.
Obrigado, Gabriel. Perguntas?
Opa, parabéns aí pela apresentação, muito legal. A dúvida que eu tenho é principalmente sobre as diferentes métodos analíticos, né, nessas duas etapas dos processos. Então, quando você está já numa lavra, você tem métodos diferentes da época que você fez o seu primeiro modelo, etc. e tal. Então, principalmente você falando em ouro a precisão desses dois métodos, se você acha que isso atrapalha ou se tem desafios em volta dessa questão.
Você está se referindo, por exemplo, se eu utilizar um modelo e, por exemplo, o modelo de blocos, por exemplo, o modelo anterior está datado, precisa atualizar.
Não, dos próprios métodos analíticos e dos intervalos de confiança e da precisão do método analítico em si. Então, você tem diferentes, como que eu posso falar, as fences, né? Eu esqueci em português. As fences que você consegue usar. Então, por exemplo, o método analítico mais rápido, ele vai trazer os intervalos low grade maiores. Né? Então, mesmo que seja um blend, né? Depois da planta, ele vai ser valores diferentes, né? Mas é mais essa questão mesmo, um pensamento que eu tive durante essa sua apresentação.
Eu acho que eu entendi. Conforme você vai realizando a operação, você vai adicionando incertezas, né? Por exemplo, tem a questão de diluição operacional, que é muito difícil de rastrear. A gente está criando um sistema para poder rastrear isso, né? A gente está considerando algumas questões para levantar esse tipo de informação para enriquecer o modelo. Conforme mais dados você vai colocando, mais mais fácil dos modelos contornar essas situações. Então, a grande cartado, o grande trunfo das inteligências artificiais é contornar essas incertezas. A gente tem muita incerteza que a gente não consegue lidar, que esses modelos conseguem lidar bem. Porém, é muito importante você ter boas práticas em relação ao uso dessas informações. Então, por exemplo, você citou ali que se você fazer uma análise mais rápida, vai priorizar o low grade, tudo. Então é muito importante saber o que você está fazendo e qual que é o impacto que vai ter no modelo. Então aí acaba sendo, aí muda um pouco da função do geólogo, do engenheiro de machine learning, por isso ele entender o que está acontecendo e conseguir fazer sentido com o machine learning. Né?
Tem o próprio efeito do também, né?
O efeito do Pita é bravo.
Aí atrapalha essas relações com você.
Atrapalha bastante, atrapalha bastante. Ouro é muito mais difícil, tanto é que a maioria dos exemplos que eu encontro é cobre, carvão, base metals, coisas mais simples. Ouro, ele tem uma grande dificuldade que é esse nosso efeito pepita, né? Então, a gente ainda não alcançou esse ciclo fechado ainda, porque a gente tinha essas questões de rastreabilidade da informação, a gente está resolvendo, e agora a gente vai começar a testar os primeiros modelos. Então, nem tem como falar, olha, isso aí pro ouro está dando certo. Não, a gente está testando na minha pesquisa agora. E, então, tanto é que eu não consigo falar muito, porque eu ainda estou criando os modelos. Eu estou fazendo a coleta, a gestão, identificando como eles estão fazendo esse blend, porque, querendo ou não, tem muito problema operacional. A gente está pegando imagem de drone, né, do pátio, então a gente compara com dois períodos diferentes. Então a gente estava identificando que o pessoal estava escavando mais do que a base das pilhas. Então eles estavam diluindo o minério na alimentação da planta com a base do pátio. Então, às vezes, o exercício de implementar um projeto desse de análise de dados, você vai descobrindo umas fontes de certezas que você não imagina na operação que você não está lá no dia a dia, que acontece. Por exemplo, sinal de sobrescalar, diluição operacional no pátio. Deixa eu só botar o slide. Erro de destino aqui, ó, você está vendo aqui que tem estéreo. Teve 5 erros de destino, onde o pessoal jogou estéreo, onde não deveria, que devia ser aqui high grade. Então, existe uma série de coisas que o exercício de fazer essa machine learning, análise de dados, de você coletar, visualizar, você já vai descobrindo essas questões, vai resolvendo. E aí o modelo, conforme você vai melhorando a qualidade dos dados, os modelos vão ficando mais precisos. Então, não é só... Por isso que eu falei que muda a lógica de trabalho. Você não fica só preocupado em saber se o modelo está certo ou errado, mas o que está provocando esses problemas. E aí você vai ter uma ação proativa para poder resolver essas questões. E aí cabe ao geólogo, o engenheiro de minas, o profissional ali, ter um olho, ter um filho, ter um conhecimento para identificar quais são as questões ali envolvidas e tomar ações. E ficar menos focado no trabalho de simulação, deixa a inteligência artificial fazer e fique focado na qualidade da coleta, na amostragem, nas análises, fazer o que aquecer, ter essas rotinas.
Parabéns pelo trabalho, muito legal. Pensando no modelo de curto prazo, né, que outras variáveis você consegue colocar no seu modelo, além do teor? Porque só o teor pode gerar um bias, né, pode gerar um enviesamento.
Qualquer informação que tiver no modelo de blocos, a gente consegue rastrear, né? E, por exemplo, litologia, dados geometalúrgicos, se tiver. Por exemplo, a gente está imaginando agora o Maurício Beckmann, professor lá da Poli, né, na parte de evidência de minério, ele criou um processo de você fazer ensaio para estimar um WI, Work Index, com 200 gramas de massa. Você coletar uma amostra de 200 gramas, você faz um ensaio ali. Então, se você pegar amostras de perfuração, de chip de perfuração, ou algumas amostras de mão da frente de lavra ali, fazer esse ensaio que ele faz, a gente consegue adicionar esses dados geometalúrgicos e adicionar ele ao modelo. Isso daí vai fornece informação para fazer um modelo preditivo de produção de moinho. Se você pegar dado de perfuração de bancadas, pegar a velocidade da perfuratriz georreferenciado, você consegue ter uma noção da dureza do material, da resistividade dele, e fazer modelos de predição de moinho também. Então dá para juntar tanto os modelos dados da informação geológica e o operacional daquela frente de lavra e adicionar. Duro é rastreado, da bancada até a alimentação. O que está saindo ali, está chegando ali, como está chegando na planta. Esse é um grande desafio que eu vejo aí que precisa ser superado.
Mas aquele modelo que você apresentou foi aquela evolução do modelo, né?
Aquele ali é um paper que não é meu. Opa, desliguei aqui, peraí.
Foi só baseado naquilo, foi esse? Não.
Isso daqui é só com um furo de volte.
Esse. Você conseguiu já testar incorporar mais variáveis no modelo para gerar
Não.
resultado?
O foco do meu trabalho hoje é gerar a engenharia, é ligar esses pontos e deixar o dado disponível. Ainda falta fazer essas simulações, tá? Mas a gente está caminhando para isso.
Opa,
Tudo bom?
beleza, parabéns aí pelo trabalho. Nesse slide aí eu tenho uma dúvida. O modelo B, o autor fala de sensores. O que são esses sensores que estão aéreo?
Não. Na verdade, essa base de dados aqui é uma base de dados conhecida, não é um caso real. Ele pega uma base de dados, que eu esqueci da origem, mas ele pega uma base de dados desse modelo e ele vai adicionando informações como se fosse uma análise pontual.
Amostra, né?
Como se fosse uma amostra. Tipo, o que ele faz? Aqui, por exemplo, ele pegou esse gabarito e ele apagou os pontos, deixando os pontos espaçados, igualmente espaçados, como se fosse uma perfuração de curto prazo, uma malha. E aí ele vai adicionando como se fosse o equipamento lá estimulando. Pode ser uma difração de raio-x pontual, ou análise pode ser qualquer uma. Existem algumas tecnologias, né? Pode ser, mas principalmente relacionado à difração.
São novas amostras que fez um novo grid de amostragem aí, no simulado 1.
No simulado 1, o que ele faz? Ele tem esse grau de truth que é a base de dados completa. Né? Ele baixou pronto, ele tem essa base. O que ele fez? Ele excluiu todos os pontos dessa base e deixou só os pontos como se fosse uma malha quadriculada. Que aí ele foi simulando os modelos deles a partir desses dados já prontos. Então aqui tem um gabarito para comparar, olha, o modelo foi bem ou foi mal baseado nesse gabarito que ele já tinha. Então ele foi adicionando novas informações desse gabarito ao longo dos ensaios do teste, como se fosse informação do moinho ou como se fosse informação já referenciada espacial, desses equipamentos. O Bendorf, ele tem um artigo que ele explica muito bem esse conceito, voltado para carvão. Carvão é muito simples, né? É uma camada única, pouca variabilidade. Então aí ele simula equipamentos que conseguem fazer análises pontuais e foi daí que eles se basearam para fazer esse estudo. Isso aqui é feito não é com dado operacional, com a base de dados já existente.
Tá, e outra questão, obrigado. Naquela que você estava antes das amostras na pilha lá, isso aí. Você contar um pouco mais para a gente como que é esse sistema de casar o modelo de blocos com o despacho e se esse ponto, a cor aí é do modelo ou se você tem alguma análise em cima disso. Ou isso, porque minha questão é se isso aí não pode ser uma decisão do operador lá. Falou, não, aqui estava um modelo estéreo, mas eu vi que é um minério, ao contrário.
Perfeito. Ótima pergunta. Então, esse modelo foi desenvolvido por mim, junto com uma startup canadense, para uma mineradora de ouro. E o que a gente faz? Existe um sistema que eles chamam de sistema de liberação. Então, toda vez que você vai ter uma frente de Labra, eles falam, essa aqui é a frente de Labra da cota 325 da liberação 1. E aí eles fazem subdivisões, que vai ter uma parte que vai ser de alto teor, de médio teor, e durante a operação, o pessoal do despacho recebe o destino pelo CCP, que é o Centro de Controle, e indica o destino do caminhoneiro lá. E aí o pessoal faz o carregamento. Lá ele aponta o que ele está carregando, então depende muito do apontamento manual. Então a gente fez esse sistema aqui muito mais para monitorar se o pessoal está fazendo os apontamentos certos. Então a gente não vê só o destino e a origem, né? A gente não vê só o destino, a gente vê a origem também. Então a gente consegue ver onde ele carregou, onde ele descarregou, qual foi a escavadeira que carregou ele, porque o pessoal fala assim, olha, a escavadeira 1 vai carregar essa porção aqui que a geologia falou que é high grade. Então vai lá, carrega o caminhão, ele registra que está sendo carregado de high grade, a gente pega as coordenadas do caminhão e plota. Só que como a gente une as coisas, né? No sistema, no planejamento de Labra, de curto prazo, eles desenham os sólidos da bancada. E eles fazem essas subdivisões. Então, meu sistema, pelo nome da liberação, eu pego esse sólido, eu pego o modelo de blocos e vejo quais são os blocos que estão dentro desse sólido. E aí, eu tiro as medidas que eu preciso, a média, as proporções do que eu estou vendo, proporções de litologia, a média de teor, a densidade média, e associo essa informação à viagem. E aí eu ploto no sistema. Eu tenho um modelo um pouco mais avançado, que eu tenho um modelo de blocos do pátio também. Então, conforme vai alimentando, eu tenho um grid que vai falando por setor qual que é o teor médio ali, a partir dos vasculamentos que foram realizados ali.
E o carregamento você faz a cada pasada da carregadeira?
Então, esse é o desafio do 1. É feito por par carregadeira, as pás carregadeiras também tem GPS e eles fazem lá. Porém, o nível de apontamento da pá carregadeira é muito ruim, porque o cara faz muita viagem. Então, o cara, na hora que encostar lá, apertar o botão e lembrar que tem que apertar, tem muito erro. Então, geralmente, o pessoal aponta tudo aqui ó, na boca do gritador. Então, eu não consigo saber como que é a retomada. O que a gente fez? A gente pega uma imagem de drone, a gente tem a superfície 3D, compara com o anterior, e a gente vê o volume que saiu. Nessas áreas que saiu o volume, a gente vê os pontos que estão dentro desse volume e fala, olha, desse período, no período entre essas tomadas, entrou X material e saiu tanto material pela diferença das topografias. Essa saída de material, a gente faz um last in, first out, porque quem chegou primeiro ele vai sendo sobreposto por outros materiais, e aí a gente calcula o que está entrando, aí para fechar esse ciclo. Então a gente está fechando esse ciclo, está implementando para poder alcançar isso daqui, poder fazer a reconciliação automática e ter o modelo preditivo e comparar o predido e o medido, que aí é onde vai ter os ganhos.
Muito obrigado, parabéns.
Obrigado.
Mais perguntas?
Foi muito legal. Eu queria convidar, inclusive, para você assistir a minha amanhã, que eu vou falar um monte de coisa complementar sobre a qualidade do dado e é o ponto crítico mesmo, né? Eu queria que você contasse um pouco das linhas de pesquisa de vocês lá no NAP, com inteligência artificial e outros assuntos relacionados.
Perfeito, perfeito. Obrigado pela pergunta. O NAP hoje, ele atua principalmente com mineração de pequena escala. Hoje a gente tem um produto no NAP muito interessante. Até chama a nossa atenção, tem um trabalho ali embaixo publicado que é de identificação de garimpos ilegais, né? Então a gente tem um programa lá que a Bárbara ajudou a fazer, ela também é membro do NAP, e que consiste em identificar garimpos legais. Então a gente está iniciando os estudos para poder utilizar a inteligência artificial para poder identificar se aquela região tem mineração ou não, porque você tem muita PLG que não tem mineração. Tá lá com RAW, você vai ver o polígono ali, não tem nada, não tem cava, não tem planta. Então, utilizar a inteligência artificial para poder identificar dentro desses polígonos se a operação é algo que a gente está começando a estudar. A gente está estudando essa questão de fechar o ciclo, modelos preditivos de produção de moinho, com informação do modelo geológico e também os dados de perfuração. A gente está também muito voltado para a parte de planejamento estocástico de mina. E tem outros membros aqui do NAP também, tem o IRFAN, a Gabi e o Rafael também são pesquisadores do NAP, que também estão trabalhando comigo na parte de inteligência artificial. E o IRFAN, que faz a parte de assessoramento remoto também. Então a gente está tentando associar inteligência artificial a todas essas áreas aí de pesquisa que a gente está atuando. Mas hoje, o meu trabalho do Rafael e da Gabi é voltado mais para essa questão de fechar esse ciclo de controle. A gente já começou com um trabalho, um projeto em Verapi, pelo Laboratório Tecnogreen, que fica na Engenharia Química, com parceria com 2 startups canadenses, onde a gente vinha com a parte teórica do que pode ser aplicado e eles desenvolveram produtos em cima da nossa pesquisa. Então, essa imagem aqui, ela é parte de um produto que a gente desenvolveu para ter a rastreabilidade da informação, para gerar dados melhores, para ser um modelo de estoque, e aí a gente conseguir avançar para esse ciclo controle fechado de controle semiautomático.
Perguntas? Mais perguntas?
Eu tenho uma pergunta, na verdade, que acaba continuando as anteriores. Você tem um case aí de exploração a céu aberto. Você entende que, em adaptando sensores ou a forma de monitoramento, você conseguiria fazer esse mesmo tipo de processo em galerias, por exemplo?
É um desafio maior em relação ao posicionamento, georreferenciamento. Esse é o desafio. Essa é a grande questão. Quando você está em galeria subterrânea, você não tem o sinal de GPS, que ele é perdido. Então, se você consegue ter alguma tecnologia que você consegue georreferenciar, Como eu só trabalho em combinação aberta, eu não sei se há, não é da minha área de pesquisa. Porém, se tiver como, a gente consegue já oferecer, mas a questão da lábio subterrânea tem uma vantagem que é uma lavra muito mais seletiva. Então, se você tem a frente de lábio aí na subterrânea, você tem aquele polígono, se você falar que a viagem do caminhão saiu dali e você tem um bom controle de um sistema de despacho, talvez você não precise desse posicionamento de GPS. Então, a gente consegue adaptar a batida horizontal de cada método. Então, pela lavra subterrânea ser mais seletivo, você ir mais no minério, e você ter esses sólidos bem definidos, a gente consegue correlacionar sim, porém, a gente não vai ter exatamente onde o caminhão carregou, a gente vai ter que estar na confiança do sistema que está indicando corretamente, e aí muda um pouco a prática, né? No lugar de a gente olhar a opção de GPS, a gente vai ter que ver o posicionamento, estar muito mais em contato com o operador, para entender se a origem da informação está correta. Então aí muda um pouco a forma, né? Mas a questão das lavras subterrâneas ser mais seletiva, mais precisa, então traz mais qualidade para a informação do dado.
Dentro das galerias, você tem os trilhos, geralmente por carros em trilhos, então você pode colocar sensores neles e fazer posicionamento relativo ao local.
Legal.
Então, dá para adaptar. Por isso que, assim, pensando nisso, eu fiz um campo no ano passado, lá na mina da Turmalina, Paraíba, por exemplo. E é um negócio que, esse caso que você apresenta, seria um case fundamental para aplicar numa mina daquela, por exemplo. Que é uma mina semi-artesanal, ainda apesar de ter mais de 30 anos de exploração, mas tem um descontrole absurdo, né, mesmo sendo em galerias, trabalhando com pegmatitos ali embaixo. Tá? Obrigado. Mais alguma questão, alguma pergunta, dúvidas? Então, Gabriel, muitíssimo obrigado. Vou continuar aí para ver as próximas. Nós temos um pouquinho de tempo, teremos aí 15 minutinhos até o início da próxima palestra. Fiquem à vontade para dar uma volta ou ficar aqui no ar-condicionado escondido do calor, que eu recomendo bastante. Nós teremos às 15 horas, o Urban, os organizadores também aqui do nosso evento, apresentando o trabalho dele. Então, daqui a pouquinho a gente está de volta. Obrigado.
testando.
Obrigado.
So it's a pleasure to introduce the Professor Ewan Logan, my supervisor. So I would like to thank him to take his time to come to Brazil. He's one of the people involved in this event, and he'll be talking about AI applied to earth sciences, a tour of our best projects. So just a small introduction of the Professor Ewan Logan. Well, he's the professor at the INRS, the Institut National de la Recherche Scientifique. He works on data science, artificial intelligence in general, and geostatistics, and his background is on geophysics and geostatistics. So, well, welcome, Professor, and have a nice talk.
Thank you. Thank you, Victor. So I'm very happy to be here. We'll start right away. So today I will present our past projects that we have done in the last 15 years in artificial intelligence or machine learning, I should say. And obviously, research is not one-man show. Actually, I'm a professor, so I'm not working at all. I'm just supervising students. Victor is one of among them. And thank you for resilient to let Victor come to us. That's a super strong student. So this is a list of people we are working with. Our partner also, GeoStacks, is a startup that has been out from our lab, working a lot in machine learning also for 15 years, and Natural Resources Canada, and also want to thank the Ministry of Economy of Quebec and the Ministry of Natural Resources of Brazil for the funding of this event. So why machine learning now? Well, first is AI community is a super open community, so you can basically all the codes are open source. So in Google, Meta, all these researchers release their code for free, which is super convenient. The other thing is the availability of GPUs. Now you can have a very strong GPU for a couple of thousands of Canadian dollars, which was not the case a couple of years ago. And if you look like 15 years ago, there were no GPU basically. And we went through what they call the winter of machine learning between 1985 to 2000 or something. And basically it's when Jan Goodfellow code the first time machine learning on GPUs. Reason for that is because for machine learning, you can do a lot of small computing operation that can be spread on the GPUs. GPUs are really slow memory, but very fast and a lot of capable, to do a lot of small computation. So GPU was a game changer for that. And the other reason is new type of data. So we switch from a very low data field to now a lot of data field. We cannot say big data, but there is a lot of data available now. So core picture, hyperspectrals is becoming more and more popular. Airborne geophysics, which is known, but also satellite data. And new sensors. I will talk about the Lamron, but you can find a lot of them now in the commercial possibilities. And yeah, so all now the challenge is to combine all those data together with the core samples. So one of the tools that has been developed by one of my colleagues is called the Lamrock. It's basically a multi-sensor code logger. You can put the trailer near a core shack or near new drillings and acquire a lot of physical, chemical data in real time. What it looks like from the inside is that you have, so the core are there, they are put on a rail, pushed through different sensors, and basically you can get like about 100 data or 100 variable in a very short period of time. So I will switch now to the examples. First examples coming from the data from the Lamrock I just showed you. So this is the kind of data you can get from this type of sensor called logger. So from the fourth row column, to the right, you have a couple of those data. And the challenge now is what can we do with all those data? So as we said for yesterday in the workshop, the human brain is not good to work with more than 3 variables at a time. Even 3 variables, they are very difficult to interpret. But the machine has not such a problem. You can put thousands of variables, and if there is a relation, statistical relation between them, the machine will learn eventually if you show enough examples. And why it is important is when you do call logging, there's too many variables. Say. It's very complex to interpret, but also it's user dependent. So actually, if you look to a mine over its lifetime, you have most of the time you have a huge change of the description of the lithology from the starting of the mine to the end of the mine, which render those databases not usable for machine learning. So it's very important to have a standardized interpretation of all the data. And this morning, Camilla talked about formatting. There is no data format in geosciences which prevent the use of machine learning also. This is super important. Data quality, data formatting, and standardization. And we have a specialist of that issue here. So for that example, we use random forest. Random forest is very simple idea, but very clever. The idea is to use short classification trees and make so the classification and make a vote at the end of the day from all the small trees that we have trained. And the results of it is shown on that slide. So on the machine learning, we used 98 variables. We trained on some wells, and we hide the other ones. So this one was hidden for testing. And the important thing is those 3 columns. So you can see that this is the core logging from the company. This is the core logging from the students who spent a month and a half to relog all the core with the knowledge of the mine at that time. And this is the prediction from the machine in about 10 seconds. So once you have enough data, you can train.
Try to speak a little louder because people will need to learn into.
Fuck them. Okay, I'll try. Yeah. So yeah, I tried to speak louder. Sorry. So the idea here was to generate lithologies based on those secondary variables, and what we have shown here in that example is that we can recreate the logs like with more accuracy than the conventional geologists on the field. And the other thing that is super important is now, as we said yesterday, you can focus. If you are a geologist, you don't want to spend 90% of your time to interpret things that you know. You know, if you see a basalt, all the geologists will recognize basalt. But if you have some differences, then you can focus your attention on those differences. And those differences require your knowledge about the settings. This morning, I think I understood it about geological setting. It's super important. So if the geologist has that in mind, and he can add this value to the interpretation of the machine. And the machine can be fed by the geologist, and the geologist can feed the machine can feed the geologist backward. Another example, just to show that it works well, so we can see that the machine classifies better than the geologist on the field. Another example, so this data also why it's interesting to have this standardized format and standardized data because they can be used at multiple time for different goals. So a couple of years later, we were contacted by the company and they say, can we train a model to interpret alteration? So we tried. So it's based in Canada or in Quebec, more precisely. And the idea is to map the content of sodium based on different variables from the lab rock I just showed you. So the idea, again, here we used a simple extreme random boosting, I think if I remember well. And we trained the model to fit the blue dots, which are measured sodium concentration only in the lab. And the prediction obviously is much higher resolution because we have measurement of the lamella every 15 centimeters, but it fits the general trend of the sodium. So basically, we can claim that this this tool can map alteration. And if you have the alteration or the degree of alteration, you can draw a vector for exploration. So it was pretty. What? Another thing that maybe you can take home with you, very simple operation can change your interpretation. So on the left, we did the classification using random forest based on the raw data. And you can see that the correlation is very high. So we have about 93%. And on the left, we simply did a center log ratio transformation. But what is important is here, when you look at the feature importance, so it's a classification of the importance of the feature for this classification or regression. You can see that for when you use the raw data, you have the strontium as the most important value, which makes no sense from the geologist. I mean, for me, I don't know, but for the geologist, it makes no sense. When we do the same for center log ratio data, magnesium was the first feature, so it makes more sense. So you can have a feedback also with the machine. You can change, you can do feature engineering with your variables, and then with those tools, you can do an interpretation based on your geological knowledge. Another example, again, on logs. So this time we used petrophysical logs, so tools in a well. It's a gold project based in Manitoba, Canada. The company name is Período, and these are different. It's a VMS deposit, and the colored lenses are different layer from the model from the geologist. And in the center, you have a well with the assays on the left. So this is the gold content measured in the lab. And everything that is in red is above the threshold. It's meaning that it's mineable, economically mineable. So the GGI, the company, acquired the data. And this is the kind of, again, data that you can get: resistivity, conductivity, IB, magnetic susceptibility, natural gamma, neutron, seismic property, and density. And again, it's very, very difficult. If I give you those data, it will be very difficult for you to make an interpretation visually. So what geologists do, petroleum industry, but they work for years to develop simple relations to get an inference of porosity, water content, whatever. But in mining, this petrophysics doesn't exist. I mean, really, that's really a shame. That's something that we should put more effort into petrophysics. But, you know, and so what we did here again, we used very simple tool, random forest, and this is the feature importance again for the gold prediction. And what we can see here is that none of the most important feature are the original feature. What we did on those data, we compute simple statistics based on the moving windows. So we compute the maximum, minimum, average, variance, skewness, kurtosis on those sliding windows. And it appears that those variables are the most important in the classification. And it makes sense, because it is a representation not only of the value, but also the features or the way the variables are moving on the window. So it's some kind of a representation of the texture of the geophysical data more than just the value itself. So that's another thing to take home if you want to do ensemble method. It's very important to work on your data and to do feature engineering. Simple tools can very help your chance of success. As building the database is the most joyful moment in the life of a data scientist, Why not using multiple algorithm? So it's another take home, I think, from our experience. Is as soon as you have your CSV or whatever you use, you can train multiple algorithms. So here, for this example, we train Kenner's neighbors, based SVM, classical decision trees, random forest, and extreme random busting. For all those algorithms, it's just 2 lines of command in Python. And you can see that there is not such a dramatic change from the most simple one, which is KNN, to extreme random boosting. We have an improvement about 10%, which is not extreme. So it's not because you have the new tool that it works better than the old ones. So the results, on the left, you have the assays measured in the lab. In the middle, you have the produced one from our methodology. On the right, this is the goal that is above the threshold. So nothing to say here. The story that I like to repeat many times, I know, like I'm an old rock star. So we presented this example in 2017 in conference, and I finished my presentation saying that sometimes we predict gold where there is no gold in the assays, but the guys from the company after the conference say, oh, but we measured gold after. It's just because we didn't measure it there. So now they're using that tool in their mind or as a daily basis. It's very rare to have success. So when we have one, we publicize it. Another example, again on core. So the idea of this example is a bit more complex in terms of deployment. Is how to interpret geology, fractures, and vein using core pictures. And so here, the algorithm is a bit more complex and it requires more data. It's a bit tricky to implement, but it's basically based on mask-R-CNN, so it's a convolutional neural network. It's known for autonomous car driving or cat and dogs identification. You can play with pictures if you want. Very easy, very fun to test with your own picture. And but again, it's not completely true or accurate. So this is the mascot of our Natural Resource Canada. So they have a mascot, and we make fun of them for that. But if you look at the classification of this mascot, it's 10% fire hydrant and 20% a person. So the prediction is not accurate. So you need to be very careful when you train those algorithms. And that's why geological interpretation and validation is super important. So for machine learning, you need a geologist. I know it's unfortunate, but that's why not. So the architecture is not ours. It's the mask-R-CNN. We just adapted the code. So again, one of the things that's super cool is what we call the backbone. So there is a lot of convolutional nets that have been trained and labeled with millions of images. So ResNet is one of them. And the weights of these convolutional nets are saved and you can download it. So interpreting cats and dogs or finding cats and dogs and differentiate the geology has a lot of connection one to another. They all have edges, they all have changing colors, they all have this texture analysis. So we can use those backbones at a starting point. So that means that they have already been trained to do some part of the project. You show the architecture, your own images, and you will have a lot to the prediction success. And what is a convolutional net? So thanks to Mathieu Sédou, it's very simple. The idea is to get an image from the left, to find a way to decompose the image on its most important features, and to try to reproduce it. So basically, it's a super compression tool for images. So how it works? in our case. So for training this network, we have examples that have been labeled by highly trained geologists. And we have filters. So these are convolutional filters. And we want to optimize those filters to recognize the rocks that are on the left. And on the top right, this is the loss function. So how the architecture or the algorithm learn. And we hope it will learn by decreasing the value or discrepancy between predicted geology and the real ones. So you can see during the training, the filters are updated and you get better and better. And after some point, you're good. And you want to test your algorithm on unseen data. Again, we are working with geological problems, so there is a lot of spatial correlation. The data splitting is super important. We need to take that into account. So for us, we train on some wells, and we will test on other wells that are not correlated, spatially speaking. So what you do, you show a rock sample, and you pass those rock samples to the filters. And at the end, the machine is able to make a prediction, and the majority voting will say that it will be a fracture for that case, for example. So this is basically how the CNN works. So if we look at the results of Medictor, on the left you have the original image. On the right you have on yellow you have the prediction of the realgar, which is the orange anomalies of the core samples. So you see that it's quite accurate, but there's still, it's an ongoing project, so there is still improvement to do. But those algorithms works particularly well for veins. Right? As you can see on the right, all the yellow lines are related to veins and fractures. It's super efficient to find fractures in rock samples. So we are now over for the core examples, where I will switch to copper deposit targeting using geophysical, geological, and geochemical data. It's a work done by Daniel Zon last year. So the idea, so this is the province of Quebec, and the idea was to demonstrate if it was possible to target copper anomalies using existing data on the national database. And we concentrate on different regions. So we work on 5 regions, so as you can see here. And we will go through the implementation right away. So we use multiple data, as I said. So we used distance to fault. We also used distance to lineament. We also used the surface geology. So we I think we had 5 or 6 layers of geological features that Danny built by hand. He has to do it as he's a geologist. He went through the most important feature that he think was important for that purpose. We used also the available geophysical data. So in Canada, in Quebec particularly, we have high-resolution magnetic maps that are available at on the entire province. So we used those data. And we also used the different geochemical data that were available in the database. So there is in here, what we did is we didn't use directly the chemical data by themselves. We basically use ratios that are known by geologists. So we have a CCPI, IUI, and so on. So we use all those variables together. And the idea again is to target copper deposits in the province of Quebec. So we had a transfer learning strategy, because if you train a model if you have to retrain a model for each region, it doesn't make any sense. So ideally, you would like to train a model in a region and apply it in the others. and that will increase your chance of success. So the first strategy was to train on the left and predict on the right. And then the other strategy that we'll show later will be to train on that region and apply it to the other region without retraining. So that's illustrate as just what I just said. So the first example will be to train on 1B and apply on 1A. And the other way of transfer learning will be to train on 1B and to apply on the other region without training. And these are the results. So on the left, you have the first training. So in red, you have the probability of copper showing. And in the black triangles are the existing copper deposits. And on the right, you have the transfer learning based on the second strategy, meaning that we train on 1A, 1B, and we apply to the other region without retraining. To our surprise, it was better to do the second strategy. We're still struggling to understand why, but the paper has been published, so too late. And one thing that is interesting also with random forest, you can also not only check the average, you can also check the variance. So it gives you a flavor of the uncertainty associated with your prediction. So on the bottom, you have the variance of the prediction from the random forest. The other super interesting way to see the feature importance is the SHAP index. So I won't explain the SHAP index here, but basically it classifies the features in terms of their importance from top to bottom, and also classify if the influence is positive or negative, depending on the casting of different trees. So compared to the feature importance that I showed you before, it's way more accurate to represent the feature importance of your machine learning algorithm. So now we switch to another topic. This one is basically how to improve the geophysical resolution from low to high resolution for, in this case, airborne magnetic maps. So the example is shown here. What we have in the entire province of Quebec, we have low resolution map maps. And at some location, companies have acquired high resolution map. And for our geologist friends, they ask us if we could apply SRGAN, basically super resolution generative artificial network, to convert all the low resolution map to high resolution. So the basic idea here, we train our model on the northern region of Quebec, and we will apply as a testing set the southern region of Quebec. And at some location, it doesn't appear very well, but the red shapes here are the location where we have both low and high resolution maps. So, and just have a look on how it looks with your own eyes. This is a tile of low resolution, and this is a real measured high resolution map. And same here. So you can see that there is much more detail. Basically, the distance between the line for resolution, low resolution is 300 meters, and for high resolution, it's about like 100 meters or 75 meters. So we use known architecture. It's called super resolution GAN, and we adapted slightly. And the general purpose of the architecture is first, on the left here, for the first network, you have as an input the low resolution, and you will try to use a generator, basically a coordinate, that will generate the high resolution. Then this high resolution will be sent to the discriminator, as well as the real high resolution data. And at the end of this network, this network will say if the generated high resolution is real or not. So it's like, it will basically, this network try to verify that network, and this network here trying to fool this network here. So it's like if you have a fake painter that wants to paint a Gauguin or a Picasso, and so this will be the fake painter on the top, and here the specialist that will try to find out if it's a fake or real Picasso. So we have to adapt it a bit for the architecture, especially because of the discriminator loss. So it's a network. So the same thing I showed you for the pictures and lithology identification. You have a loss function, and ideally the loss function goes slowly like that. But here we can see on the discriminator that the discriminator doesn't learn nothing after 20 epochs. So we have to trick a bit the architecture by not putting the two. Basically we put this algorithm not adversarial. So we, instead of make the two network in conference, we try to make them help with each other. And at the end of the day, this is the result of the training set. So again, I repeat that in the northern part, this is of Quebec, this is the training sets, and we have the low resolution here, the measured high resolution, and this is the generated high resolution from that image. And that's something that we saw in almost all our project is deep learning architectures are really, really good to learn. So if you show them an example, it will be very good to reproduce it. But that's not very interesting when you want to do transfer learning, so applying to another location. But that's something that is also known and recognized in the industry of machine learning in general. Deep learning are really good learners. Like ChatGPT is super good to reproduce what you saw before. If you place ChatGPT in a situation you never saw before, it will fail. That's why when you make a request in ChatGPT, you can fail. Like one of the things I've done is to ask ChatGPT to write my curriculum, and so it started very well. I'm a very renowned professor, so I was pretty happy. But then it's switched to say that I was really good in ecosystem modeling and water or something. So it's really good again to repeat what you have seen in the web, but my CV is not in the web, so it will maybe fail. And that's another thing. I really like ChatGPTs, and I think it will change the world by a lot of positive ways. And all for the students, I think it's super interesting to test your knowledge with ChatGPT. So if you can see that ChatGPT lied, that means that you learn a lot. And if you can see that your supervisor lied, well, I'll stop there.
And if you know how to make the good questions.
Exactly. So for the testing part, we test on the southern part of Quebec. And here you have the relation between the low resolution.
Yes, huh? The video is extended to here, so you have to be careful.
Okay, thanks. So you have the low resolution, the real one, and the measured one. So you can see that the super resolution GAN can also correct the bias of the high resolution compared to the low resolution. And what is interesting for the geologist is it also increased some interesting parts. So, for example, lineaments that appear more clearly, faults also appear more clearly. And in general, boundaries are way more sharp when you use the super resolution magnetic maps compared to the low resolution ones. So our colleagues at the Natural Resources Canada were pretty happy to use that for their own projects. This project is a bit like, I think it's the most advanced one with the project that Victor will present tomorrow. Here we tried as a crazy test if we could replace 3D inversion of MAC data using deep learning. So the idea is to take the 2D maps from airborne magnetics and to get a 3D models of the susceptibility. One of the problems in the earth sciences, and it's an almost general problem, there is no true data. So if you go to even the core samples, I said a lithology. Lithology is a description of a geologist. So he has a model in mind, and might not be accurate, or his model can change over time. So it's interpretation. So one of the way we did to treat that issue is to use our knowledge of geostatistics. So in Canada, there was this huge initiative in the last 10 years. It was called Footprint. And a lot of energy have been put to build 3D models of the geology, like realistic models, like this one on the left. And also populate those models with physical properties. So GP Payment, we will talk just after me when he was at NERA Geoscience. That's what the job they've done for 3 deposits over Canada. And it was a really interesting work for, I think it's also, it should be maybe deployed more worldwide, I think. So in that area, we have a major deposit, which is called Malartic. And the idea of the whole project was to understand the geological setting of this deposit. And now, adding those data, we can use conventional geostatistical tools. Like in that case, we use multiple point geostatistics to generate multiple realization of the geology. And as each lithology has its own distribution of magnetic susceptibility, within each geological units, we simulate using sequential Gaussian simulation the distribution of the magnetic susceptibility. So at the end of the day, we using very simple geostatistical tools that are freely available on the web. You can generate like 500 and more if you want 3D model of the susceptibility. So now you have enough model to play around with deep learning. So now that you have 500 model of the magnetic susceptibility, you can also compute the synthetic airborne magnetic maps. So using simple physics, you can use geophysical forward modeling, and now you have the full 3D model of susceptibility and the associated magnetic anomaly. So you can play with deep learning now. And by the way, for those who want to play with deep learning, there are a number of papers that have been published in the last 2-3 years that have proven that training a deep learning on synthetic data works better than in real big databases. So it's a huge avenue, I think, that can be exploited in our field. So if you use like geostatistical tools that were just presented before, you can get this set of data to train your deep learning model. So once you have this data set, as I said, you can train a deep learning model. In that case, we train a res unit, so it's a node architecture for years. The only particularity is we apply a layer of attention. So attention is the base of ChatGPT or LLM, large language models. The attention layer is super interesting to find relations at different scale between different signals. So that's the reason why ChatGPT or LLM are super good at translating phrases, is because it's really good at finding spatial temporal relation. So the race unit is basically a convolutional net, the same one I showed you with the trilobite. So you decompose the image of the magnetic susceptibility map into its optimal compression, and then you decompress. And you also had an attention layer at the end of the middle of the network to ensure a multi-scale attention. So if you apply that, then this is the results that we can get. So you have the magnetic susceptibility map. We have the real susceptibility model that have never been shown to the model, because we simulate the model, we can always keep some out of the training. And this is the inverse modeling. And so there are differences, obviously, but there are a lot of anomalies or points in common, proving that the techniques work pretty well. Still need improvement, still an ongoing work, but it opens the door to 3D inversion using machine learning. And if we were really smart, which we are not, the super idea, and if you look at the paper from Joshua Benjo at Montreal University, they use that kind of loop, but like for 3-4 months in a row, they never stop. So instead of having 500 models, they generate 500,000 models, and they use those models along the way. So they're training, and they erase the models, but they can train for their models for months without stopping. And in terms of data or memory, it's very, very low, because you erase the models one after another. Just train the machine to get better and better. And we don't do that because we don't have enough computer power. So if you want to invest in a small research group, the last project has nothing to do with geosciences, but I like this project, and also it represents the opportunity that you can get if you use or if you train yourself in machine learning. So we apply machine learning for fishes detection like this, but we apply machine learning for neurosciences. We have project for multiple resolution bone detection. So data is data. As long as you have a specialist at your side, then that can tell you that you're doing wrong, you can play with the data, whatever they are. So I know nothing about fish, but we know data about machine learning. So the project was in Montreal, and they had to destroy an old bridge that were collapsing. And once they started to destroy the old bridge, they were afraid about the wealth of the fishes. And the reason is fish industry is super important in Quebec. People come from all over the world to fish our salmons. So to avoid the fish to die, they built fish paths, and they implement those fish paths with different sensors. So this is a engineering plan of the fish path. So it's a couple of tens of meters of wide, and there are 2 paths here. And those paths are instrumented with multiple sensors, so 8 cameras, electrical sensors, and others that I don't know. And so they can take pictures of the fishes that are crossing the path in different ways. So we have 8 angles for, but you don't have only fishes here. I don't know the name. It's in Loutre. Someone in Loutre. Another, which are not supposed to be in Montreal, actually. That's a surprise for the biologists. And so the idea is to train a deep neural net to recognize fishes and to recognize their species in real time. So for that, we biologists labeled 2,300 fishes by hand. And we used a very known framework, which is called YOLO, for you only look once, not what you think, guys. And this architecture is also a convolutional net. Convolutional nets are for graded data, so picture images are still the best, better than transformers still today. So we use a component to compress the fish images, and we train the model. We retrain the model with our 2,300 data. So what we have at the end. So these are the fishes. Just to let you understand what was the issue before, you see that's still boring to wait for the fish to come in 18 seconds. But imagine the poor biologist that has to look at 24 hours of videos, and there are like 10 fishes per day. That's a crazy job. And so the project went pretty well. So it can identify the fish. And you also have the probability of being these species. So here is 93%. So it still shows that the outcome is a probability. So the outcome of this architecture is what we call the softmax layer, is the probability of belonging to that species or not. The other interesting thing that we saw, we were asked actually by the biologist, as you have multiple cameras, you can also follow the fish when they cross the path. So it seems that it's very important for biologists to know where they are in the path. So this is all the path, all the colors represent one fish and where they were in the path. And here in this histogram, it's another thing that were demanded by the biologists is which direction goes the fish. So in orange, it goes downstream, and in green, it goes upstream. So you can do a lot of statistics, and you don't miss any fishes by using those technology, and you maybe save the I don't know, the health of some biologists, mental health of the biologists. Anyway. And the last project is also ongoing project, but I think that it's very promising for machine learning, especially in geosciences. If you don't have graded data, so the data are not on a regular grid, you can use graph nets. And you know all graph nets because it's the algorithm that is behind Facebook to find your best friends. So when you have friends proposition is based on graph nets. How it works, you have nodes, so the properties. So how many times you watch soccer or you watch tennis, whatever, all your activity on Facebook. And on the edges is the connection with the people that have the same interest than you. So for example, for us, we can see the nodes as wells or drill holes. And the connection is, or the edges are the connection between these drill holes. Do they share the same ethology? Are they far away one from another? All these properties that can relate those different wells. So we use, again, an architecture. It's called GNN, so graph neural nets. And basically, as an input, we have the different well properties on the left. And we compute the graph of the net or the identity matrix on the top left using the different properties of the wells. And on the right, we deal with the spatial and temporal data. And you have two layers here that are super interesting. It's called LSTM, long-term, short-term memories. It allows to handle periodic temporal signal very well. So the data we use for training are basically a 3D model of the hydraulic conductivity. So we have a synthetic model again to train, where we know the location of the well, obviously, because this is what we place the well. And we will change or vary the pumping rate of different wells to test our methodology. So we tested multiple scenarios of pumping and stopping pumping on different wells. And this is the type of connection that you can check after you first pass your wells into your connecting device or graph device. I will try to show you that it works pretty well. So on the left, you have the coordinate of the screen well, so where the wells are pumping the water. So you have the depth, X, Y, and X. And you can see that those two wells that are close to one to another, they are connected to those four wells that are connected into a very, very strong node. They are also connected. So it proves that the connection, the graph learn well how the wells are connected in spatially speaking, sorry. Now you have the spatial connections. You need to deal with the temporal issues. So as I said, you can use a GNN with LSTM, but what we have, what we tried recently, because the signal that we have are not periodic, we used transformers. And essentially in the transformers, the attention layers is the key. So basically the attention layer, if you have enough data, is an LSTM on steroid. It's super, super good to find temporal relation. And that's it.
Thank you very much, everyone. Questions?
Foi mal.
Evening. My question is about the corporate prediction model you made. And you mentioned that you used 3 different sources of data, geological, geochemical, geophysical.
Yes.
I'd like to ask if the proportion of those data affected the prediction model. So for instance, if you have an insufficient amount of geochemical data, if that could affect the quality of the prediction model?
Not in that case, because we used random forest, but it would have been a problem like for a deploying issue. And also in that case, because we have table data, so at each layer you have the same amount of, see what I mean? So you use a random forest, so you have a table, so you have no missing value.
Questions? Comments?
Hi, thanks for the presentation. So I have a question about the method that you use for upgrade the image quality. Once you need the high quality image, it's the same area, you need the high resolution. So if you don't have the high resolution, there is a solution for that. So you can use another area to train the model and then try to make a high resolution from this area. Is it possible?
That's a really good question also. Well, in computer vision, they degrade the high resolution they have. Like they use blur function or inverse Bessel function or in, but we started with that, but it's way better if you have collocated high and low resolution. And talking about if you can apply it, like for example in Brazil, what we have done in Canada, I don't know. It's an open question.
Okay, thanks so much.
Someone can try.
Yeah, young guys can try it. And the codes are freely available on GitHub. So applying, putting your own back data in is super simple.
Thank you. Congratulations of your job. My question is about the, you showed some cases of the goal targeting.
Yes.
And you use the petrophysics and other variables. And you classify as the importance, I think so. And how do you calculate this importance for each of these variables?
Yeah.
Is human or is it
No, no, no.
machine?
It's a machine. It's a part of the random forest. In that case, you have a function that calculates the feature importance, and basically it's the number of times the feature has been used for the classification. So, yeah, how much? So the feature that was the most important in the different trees was the maximum of neutral values. There is no human interaction here.
Yeah, that's the same for the SH.
Yes, exactly. I mean, in the sharp value is way more efficient than the feature importance, way more reliable than the feature importance.
Thank you.
And the codes are also in scikit-learn. You just have to write the function. It's already written for you.
Yeah.
Thanks for the presentation. Did you think that the development of foundation models could help to improve this kind of task you showed?
What do you mean about foundation model?
Foundation models to pre-train the models to after train your own data, specific data.
Yeah.
Like segmenting model, like Britvi for the NASA EBM model.
Yeah, I mean, yes, that's very interesting, and that's we have learned along the path is the more you have a well-trained model for your own task before, the better it works. Because if you wanted to train the deep neural network for SR-GAN from scratch, we will never achieve that at all, never, because ResNet has been trained on millions of data. So again, if you have an idea that you can train a model that can help you other model, then obviously yes.
Any more questions?
I have one more question for the fish detector system, because I was in vocation. I went for a place here in São Paulo that they have a project called Onça Safari, that they use images to identify, how can I say, jaguars, like the animal.
Yeah.
And they have like a lot of footage of those animals, and they have to look one by one, identify those animals, and each animal has a signature pattern of their skin.
Yes.
So I proposed to them to make a project to recognize it. Was very close what I was thinking about, like the fishes. So I'd like to know how you manage this image data to make the training section. How do you manage this data? Like you have to have a picture of each fish with the classification. How will you extract your data for image analysis like this?
There is a kaggle that has been, I think is closed now for 2 or 3 years to identify whales on pictures. So the same problem, but each whales has some, their tail is really specific, and the biologists label the whales for all the pictures they had, and there's, some people were able to detect about 99% the different whales. Yeah, and also I remember reading that paper that it changed completely the way biologists saw the behavior of the whales, because now they can't. As a biologist, it's very, very time-consuming to look at all the videos, all the pictures, and so you take samples, short samples, and you do your interpretation. But now you can have an idea of where are the whales almost in real time, and they change completely the way they see the problem.
But maybe we were trying to ask for the data set of the fishes. They took like the video frames and they labeled these video frames.
Yes.
That was.
Okay. Yeah. You obviously there is a part, the painful part. You need to label the data, or you can try unsupervised. I didn't talk about a lot because it's complex and time-consuming, but you can try. Like you can use like VAE maybe, and that the other thing. I mean, I stop after that. But There is something that is super interesting for your projects, and we are completely into that now. So these are the past projects. What we are now is into embedding. So when you compress your signal into an encoder, what you have at the end of the day is a signature of what you're looking for. And for example, for the fishes, if you look at the embedding at the center of the autoencoder, it's like the DNA of these images of fishes. And you can use this embedding. This is a very powerful way to compress and identify data. And by the way, this is what is behind your face recognition on the phone. It's an embedding of your face when you train. And then it looks at the dissimilarity between your embedding and the embedding of all the people in the world. And it says, yes, so I think there is a lot of research that can be done in that area. And it's unsupervised. Oh, no.
We can talk about it later. Just about the inversion algorithm. The paper there talks about inverting magnetic field data.
Yeah.
And one thing that came to my mind was, did they or you, I don't know if you were part of the thing, consider the effects of remanent magnetization?
No. It's a very an ongoing project. It's only synthetic. So we generate the data, we control everything, no remanency, no.
Because Canada, it's all right. You have a really large field over there, but here in Brazil, it's just a mess. So you have the South Atlantic anomaly, and you have 1/3 of your field there, and that's an issue for us.
Yeah, I mean, I think I will retire before that things works for real. But yeah, younger people will take the plane and go further.
So thank you.
No question.
No more questions. So lots of research opportunities. Okay, so thank you, everyone. We are going to the coffee break and upstairs.
Upstairs.
Yes. Thank you.
So let me introduce Jean-Philippe Paiement. So Jean-Philippe is one of the first winner on the Kaggle Championships for machine learning applied to mining. And he has a multiple knowledge, geostatistics, geology, machine learning, geophysics inversion. And now he found his own company. And I will let Jean-Philippe continue his presentation.
Yeah, thank you, everyone. I guess everyone can hear me all right?
Yes.
Good. And then you should see a screen appear right now.
Yes.
Perfect. All right, let's go. Yeah, so today's talk was sort of designed to show how AI is going to change, or how I see AI changing the way we communicate about geoscientific information. So overall, the goal of the talk is just to give examples of how the way we speak about geosciences, about geological objects, might change through the use of AI, and also because, and it's sort of a self-feeding circle there that's going to happen. Just as a mean of introduction, yeah, I'm Director of AI Mineral Targeting for Verify. We are in the process of building a web app to run targeting exercises for our clients. I personally have about 20 years of experience. I've always been a consultant, so I've seen lots of different projects. I went from exploration consulting to resource modeling to advanced geostatistics. And about 8 years ago, I sort of pioneered or started using AI for the geosciences during the Gold Rush Challenge, which was a crowdsourced targeting challenge that was put forward in Canada. And that sort of sparked the idea for me to apply different AI techniques to the geoscientific world. Since then, I've worked on different things. We have worked on supervised learning using sort of random forests for targeting, automated geological mapping using deep learning, NLP, so natural language processing for drill hole relogging, and so on and so forth. So today I'll give you 2 examples of how we apply AI to geoscience. So what I see is there's a common issue in most of the products we use to communicate around geoscientific formation. So what you're seeing here are 2 different maps. One on the left is just to show different mythologies. Yeah, so that's the one on the left. So from points, we try to draw a representation of the spatial distribution of rock types. And on the right is what people use as targeting for gold deposits. So what you're seeing is just circles on a map saying target 1, target 2. And these things are static, and the main issue I see with them is that they're sort of displayed in a deterministic fashion, meaning that if a lithology is in a polygon, it's 100% sure this is a granite, whereas there's different issues surrounding that. So one question I always been given the talk for a while, and I'll ask you guys again. I don't know how well it's going to work, but could somebody name this rock? So obviously, whenever I gave the talk, no one dared to raise their hands. And there's a reason for that, is because geosciences is somewhat subjective. So we make a decision, we label data according to our own sort of experience, our own models, a lot of cognitive bias goes into naming rocks. So if I were to ask that, the answer could be 2 ways. So traditionally, what people would say is something like that here. So this is a carbonatite. But rarely do people sort of ask this underlying question. That underlying question is, or is it? And if you've seen enough geological projects in your life, you'll see that the same rock can have numerous different names, especially when you're looking at drill hole logging or mapping, depending on the person who's mapping, depending on the year it's been mapped, depending on the underlying model you're trying to generate, the names of the rocks will change. Whereas what I think the industry should strive towards going is something like that here. So this rock has 80% chances of being a carbonatite, 10% chances of being a marble, 5% chance of being pairing gneiss, and 5% chance of it being gneiss. So essentially, you're giving a probability of an answer. So one way to do it is to look at the rock, have always 30 geologists with you. Each one gives a name, and then you do statistics on those names, and then you find out what is the most common rock name. Obviously, that's pretty impractical because walking around 30 geologists in the field could be expensive and, yeah, kind of dangerous. So these deterministic models and the way we've been labeling data in the geosciences using deterministic approaches, meaning it's that and there's no other chance that it's the reality, comes with some issue, right? So the first issue we see is there is an uncertainty in the input data we're using. So if you were to create a map like the one you see here on the screen, you'll see that the rocks have been, or the points have been colored according to their different lithological classification. And then the background map has also been colored using these points. So there are some pretty evident errors there. But one thing is we're not capturing is the uncertainty of the input data. So how certain is that label that you're using to display the color? The second thing that we're missing is how probable is the output, what's the probability of the output being accurate? So meaning if I draw a contact here on the map, how likely is that contact true? What is it based on? And that comes to the third issue with deterministic approaches is that we don't know the importance of the input in making the final output or the final decision, right? So obviously you see errors on that map all the time. So deterministic maps are often static, and we can't see really how accurate our drawing of these sort of labels or segment are according to the input data. So that's one issue we see, right? So we want to know what explains the interpretation of the contacts. How do they come about? What's the likeliness of that contact of being true? How accurate are the mapping points? None of that is captured in the way we currently use geoscientific information or currently display geoscientific information. So what is the solution then? And that's for me, so the solution goes through using instead of using deterministic approaches, is using probabilistic approaches. And probabilistic approaches are essentially just a way of displaying numerous outcome, giving changes in the input, right? So if you use a deterministic approach, like we're used to, essentially you have some input data here, you have a model, the model could be in your head, just drawing a map, and then what you get in the end are definitive answers. So these answers are that, and there's no chance of them being wrong, and there's no way to measure how accurate they are, they're just that, right? Whereas what we're trying to move the industry towards is using, again, different input parameters, a model, and statistical approaches. So instead of giving a definite answer, you give a distribution, a possibility for that answer. Essentially, you're giving a probabilistic output to your data, meaning that the reality lies somewhere inside that distribution here. So if you want to transform that into a deterministic approach, you could go and you just use the mean and say this is the answer. But what we really want is to use the probabilistic outcome to make our model. That has different applications. So how do we traditionally go about that? There's been numerous ways of transforming sort of deterministic data sets into probabilistic data sets. One way is to use conditional simulations. So the example here is you have some drill holes. So the drill holes here have been classified into two categories. So the two categories would be outside of the pegmatite dike we're trying to model, or inside the pegmatite dike. We also have the deterministic version of the model, which lies here, which is just traditional modeling section by section of your geology. But through conditional simulation, what we can generate is just a number of probable model here, right? So these models are all statistically representative of the input data, but none of them by themselves is actually true, right? What comes is the accumulation of these models. So normally you would run about 30 to 100 simulations to get your final output. And the output we get out of that is this map here. And this map is actually representing the chances of each cells in our model of being inside the pegmatite. So obviously where it's red, that has a really, really high chance of being inside the pegmatite. So there's a lot of controlling data, the statistical and sort of spatial data make it seem that way, but there's other areas where you see that it's less likely. So what that allows us is to have areas like this area here. We sort of evaluate the risk. So you see that it's somewhat inside the model, but the probability of it being a pegmatite there is around 20%, right? So that means that we're lacking information to classify this area, right? So now we have a product that can actually represent the level of risk associated to our data, and also sort of is a bit richer in terms of information. The other thing you can do it, so that was in 2D. This is an example of a probabilistic model in 3D. Here, that was used as an input to a targeting exercise. So instead of using, so basically we were targeting orogenic hosted veins, or orogenic style vein deposit in the Abitibi, and one of the main hosts is diorite. So wherever there's a diorite, you have more chances of finding these veins because it's a brittle lithology, so the deformation just makes for a better fracture system there. So one way would be to just generate a model in Leapfrog and say, well, this is diorite. But actually, we don't really know how likely is that diorite of being there. So instead, what we did is we used conditional simulations to generate a 3D model of probable location for this diorite, and this is what you're seeing as a result here. So it's just a filtered version. So each block now has a probability of being a diorite, but it could also be, so think of each block there in the model. So if I were to zoom in into one of these blocks here, so let's say we look at this block, maybe this block is 20% a diorite, but it could also be, let's say 30% being a granite, or maybe it's 50% volcanic, right? So from something that has only one input, the lithology, we're creating more level of information. We're actually creating numerous different output possibilities. Oops, sorry about that. I'll just back here. So what are the advantages of moving towards probabilistic models instead of deterministic models? Is that these probabilistic models allow for quantification of uncertainty surrounding the interpretation of the data. So essentially, we know how some areas might be more certain than others in our representation of geoscientific data, either in maps or prospectivity model or geological model. There's a better risk assessment associated with them. There is an explainability in the results as well. So we go beyond the cognitive bias and we can actually know how important are each input in making the final decision. And they just produce richer data sets to be used as input to AI-driven modeling. And that's where we'll sort of dive into the AI portion of the talk here. So I don't know how familiar you are. I haven't seen the course, so I might be repeating some stuff here. But traditionally, AI or artificial intelligence or machine learning will use probabilistic outputs to make a decision. So if you look at the image here, basically, if you run an image of a cat inside a convolutional network that's designed for image classification, what you'll get as an output is not just the final category. What you're actually getting as an output of the network is this thing here. And this is the probability of the image of belonging to every classes possible that you're trying to classify there. So you see it's a cat because it's 70% probable of being a cat. But it's also probable that it's being other things. And funny enough, it's more probable that this thing is a dog than a tiger, which is kind of interesting as well to see how these models make their decisions. And then what I put also as an example here on the left, on the right is typical output. So you see whenever we run these types of algorithms, you see that here we have a mite in the image because that's the most common or the most probable output. So these are how machine learning make their decision, right? The decision or the final answer we get from any sort of AI-driven modeling is associated to a probability, not just the final class. So we take probability space result and change them into a deterministic answer. But sometimes we might want to say that probability space, and I'll show you guys why. So, I mean, again, I see different ways that AI is going to impact our industry right now. The main one that we'll discuss today is data processing and interpretation. So Obviously, artificial intelligence is capable of handling large amount of information. It's more efficient than what we traditionally do in terms of statistical correlation. And it will allow Geoscientific to run quickly, sort of quick interpretation in complex data set. It might lead to just faster conclusion or more accurate conclusion. It also sort of improves the prediction and modeling. And again, it's a good way to move from deterministic models to probabilistic model just by using sort of the output of artificial intelligence. So what we're trying to do is just go use a lot more data into our decision making and also sort of have better accurate results. So how is that possible, and what are the different things that lead to that? I mean, one of the main things that I see in geology being sort of the emerging thing is generative artificial intelligence. So that's been around, the concept's been around for quite a few years again. It's not something new per se, it's just the computing power of computers is just getting it to where it's possible to easily train these types of models and deploy them. But neural nets have been around for a long time. The rise of like deep learning comes from the 2010s and around, where like convolutional network, image processing, and recurring networks could be implemented. And then in 2010, about the generative models started to appear. And these generative models can be really complex, can be really simple, but they all sort of function the same way. And that's by taking some sort of information, either a latent space noise data or whatever you want to feed to it, and it generates an output. So that's why it's called generative AI. So what you see is you have an input to your data here, and then through the network you get an output there, right? So it's quite easy to decipher how it works. That's an example here that's using DALL-E, and I asked DALL-E from OpenAI to draw a geologist combining AI and fieldwork, and this is what the network drew, right? It's a sort of a funny-looking geologist with some computer on his back and a quite old drone, actually. There's better drones now to conduct these mapping exercises. But anyways, it was funny to see how AI sees our work in the future, right? So there's different types of generative model, but they all sort of function the same. So again, what we have typically are input data. We have a series either convolutional or transformers or an architecture behind it that's going to process the data. The common thing in all of that would be in the middle here is what we call the latent space, and that's really interesting, and we'll see why later on. And from that latent space, you normally have either another network that's going to decode the information and produce an output, right? So these output could be anything. You can train them to do whatever you want. One way to train these generative AI is through the use of generative adversarial networks. So for me, I mean, I gave this talk, or some version of this talk, and I've been giving it for quite a number of years. GANs, or generative adversarial networks, used to be the new kid on the block, but in the last 2 years, things changed pretty quickly, and they're not actually the new kids on the block anymore. And I'll show you what is actually new. But the way these generative networks are trained is quite interesting. So you have some training sets. Obviously, most of the time you're looking at images. So what we'll do is we'll train 2 different networks at the same time. So you have to build a network that's called a generator. So that network is going to take an input data set. It could be either noise or whatever you want again. Goes to the generator, and then it generates the output. So the output looks like that. The second network we'll train is called the discriminator. And the discriminator actually has one function, and is to test the output image from the generator and the real images and see if you can decipher between each image of being true. So the network knows that this is a true image. It's trained to recognize that as being the truth. And once you've generated your sort of fake image here, you run it through the discriminator. And the goal is to have the discriminator say that the generated image is a real one. Okay, so that's through numerous training iteration. But basically, what you're trying to do there is have the generator here fool the discriminator into creating an image that can't sort of be deciphered between real or fake. And that's what we all call sort of deepfake images, right? So you're probably all familiar with that concept. So that's one of the network, sort of one of the algorithms we could use. The other one that are now the new kid on the block are large language model transformers, and I won't go into depth into how they work, but essentially, again, here it's sort of the same process. We have input data, and in the case of large language model, it's a sentence. So we say nickel deposits are often associated to ultramafic rocks. So what happens there is a first series of architecture of a neural net. In that case, it's transformers, will transform the data into a latent space. So the latent space is what you're seeing here. And each word in that latent space, each word of our sentence has a coordinate, has a specific place into that space. I think for something like ChatGPT, you're looking at more than 1,500 dimensions for that latent space, so it's quite complex. It's hard to represent in 2D, but that's just a simple image. So in that latent space, words that have sort of similar meaning are used often together will plot together, whereas words that are not often associated to the other words will plot farther apart. So that's why I put the word pants here, cat would be here, and everything related to geology would fall closer to here, right? So it separates the word into their meaning and how they're used together. And then we have a second network that's going to be built to take the latent space and reconstruct the input data, okay? So that's typical sort of, sorry, just have to plug in my iPad. So that's sort of typically how these models are trained. And they're really useful. And I'll show you an example where we could use them. I use a latent space to generate sort of probabilistic output for the geosciences. The other thing that's really a bit newer and that we've been using are vision transformer. So it's the same principle as large language model transformers, but instead of feeding in sentences, we take images as input, we break them into little tiles here that would be same as the tokens for large language model. The architecture is about the same, and what it does, it tries to classify these images, right? So again, it's going to put them into something that's really interesting to me here are these embedded patches, or the patch embedding, and that's something we could use in the future as well, and I'll show you how we use them. So again, these models are complex. They're not easy to train, but if you train them correctly, there's a real power of that latent space and to use of that latent space in making predictions using AI. So what we'll see today are two different ways we could apply artificial intelligence to our current problematic in the geosciences. One is going to be around automated geological maps. So how can we use input points to generate geological maps? That's from mapping points and remote sensing. And the other one is going to revolve around mineral system targeting, or how can we create prospectivity map using different input data, or all of the possible input data. So I'm just going to try and plug in, because otherwise I'll lose my presentation. There we go. Oops. All right, so let's dive into our first application, and the first one is going to be how we can generate geological map from semi-structured data automatically. So again, I come back with my image of all of these mapping points. So one issue we see with these points is there's a lot of information that's stuck into that database that's not really used by the geologist. So most often these points are made from mapping campaigns. So the geologist will go in the field. They're going to describe the outcrop they see, the rocks they see. They come with a lot of textual information, that's rock description. So something like fine grain, dark green rock with quartz veins, so all of that description. But in the end, what happens is we try to consolidate all of that information into a single label, and that's a unique rock code, which actually sort of loses a lot of the richness of the information. So how can we access that information? And that's what I'll show you today. So yeah, again, historically, we tend to oversimplify all of these mapping points to fit our purpose, and our purpose was to generate these polygonal geological maps that we've all seen in our work. But it could be a blocker, especially if you're looking at old district. These maps are rarely updated, so that's an issue. That once the map is made, it becomes static. Even if there's new points added to it, most often either the government instances or the companies won't update their geological maps because it's just too complicated to do. So how can we automate that process and make a product that makes more sense? So as I said, these points, so for every point in our database, what is actually really interesting is not the code. So right now, if I zoom into one of the points, oh, sorry. If I zoom into one of the points, this is the data that's associated to it, right? So if I were to use it traditionally, I would just go to this this entry here that says V4A. And since it's in Quebec and I'm familiar with the coding, I know that's a ultramafic volcanic, okay? However, what's really interesting actually lies here, okay? And that's the rock description and description of the outcrop. And one example that I can show you why this is important is because in the James Bay province of Quebec, there's been 20 years of gold exploration, okay? People have been walking around trying to map for gold exploration for 20 years or more than 20 years. And about 2 years ago, lithium pegmatites became a thing, right? And there's a lot of lithium pegmatites in these grounds, and people were walking on pegmatites in James Bay, but didn't know they were important because they were looking for gold. So there are a lot of mention of pegmatites here in the descriptions, but they're not captured in the rock code. So if you were to make like a pegmatite maps, to try to make a map of pegmatites or possible pegmatites, you wouldn't be able because you wouldn't capture that information if you use sort of the traditional oral approaches that uses the labels. So how can we change that? So what we're proposing on doing here is quite a bit more complex, and but it's fully automated and it works really well. So what we do is we take the outcrop points, and that's the mapping campaign points. The first step we'll do is we'll run these points through a large language model embedding. So what we get out of that is the positional of each word in the sentences. So if I zoom in, what we're interested in are these. So we transform the text data into a 1500 dimension vector space. So we go from text data to numerical data, and this numerical data, that vector representation of the data, can then be used as input to other sort of AI application or machine learning application. And this is what we're doing, right? So we're taking that that data set, and then we're also providing names to the lithologies we're interested in logging. So in that case here, I say, well, these are my rock of interest because I'm exploring for X. So if you're exploring for lithium pegmatites, you might not be looking for the same rock types as if you're looking for gold or if you're looking for ultramafic nickel associated. So basically, you provide your rock code of interest. What we do is through supervised learning, and that's super simple. We do a model. So what we do is from the embedded space here, we try to predict the rock names. And what we output in the final are the probability of each point of belonging to our sort of categories we're trying to find, right? So we transform the text data to a probability of each point. So if I were to look at each point here, I would say that it's 10% granite. Maybe it has 5% chances of being a volcanic, and maybe it's 85% chances of being an ultramafic. Okay, so I transform all of the text data to a probability model for the lithologies I'm looking for. Okay. From this, then what I can do is use the remote sensing data, and that's not something that's entirely new. It's been proposed elsewhere, and we're not the first one to do it. But what we're doing is from the remote sensing data here, so you could use mag, gravity, you could use DEM, aster imagery, satellite imagery. Depending on your ground condition, depending on the cover, you use the remote sensing that makes sense. You run that remote sensing through a computer vision algorithm. In that case here, it's a WNet, and it's something that's I think Victor has been also working with. So it's sort of, we're going into the same direction here. But the first, we pass it through a first convolutional network. We get the data essentially here in the latent space. From there, we add up our control points. And then a second neural net is going to recompose the data into these things. And this is what is really interesting, actually. What we get, what we get as an output here is the probability for each lithology on the map. Okay, so you're not getting a geological map. We're not really interested in reconstructing the geological map that's been constructed by a geologist. What we're interested in is what is the likeliness of finding this rock type, for example, right? And this is what I get. This is what I get as an output, is a map of the probability of finding one of the rock type of interest for me. So if we were to apply it, this is a subset of the Lagrange province in Quebec. So for that area, we have the compilation of all the mapping points. That's public data. And that's really fun because we're all working out with public data right now. So compilation of all the mapping points with the descriptions. We have high resolution magnetic data, and we have a 30-meter digital elevation model. So from there, the first step is going to be to look at all of those mapping points. So if I were to try to generate a map from the labels, I'm stuck with 1,180 individual lithological codes. So my map would include more than 1,000 lithologies. Imagine trying to model that. It's almost impossible. So I would need to go and simplify it. Manually simplifying all of these points would take me a long time. And what's most likely to happen is it's not going to happen, right? Because the geologist is going to get fed up or whatever. You don't have infinite time in your job, so you'll just drop it and never do it. So we need an automated way of simplifying the different categories. And we want to use the full extent of the data and capture really the complexity in the geology. So the first thing we do is use the OpenAI embedding API. That's almost free. You pay a few cents per token, or not even like a fraction of a cent per token. So it's not really expensive. So from these points, what we do is we get the embedded space of all of those descriptions. So right off the bat, what we see there is there are different groups in there. So if you were to zoom in, you see that my lithology description actually generate little clusters of similar data. So that means that these sort of different outcrops have descriptions that are similar to one another. And that's really interesting, right? And then what I'll do from there is look for different lithologies. So in that case here, my lithologies of interest are amphibolites, felsic intrusive, iron formation basalts, tonalite, and permanganate. So what I end up doing is I use the embedded space as features. I use the lithologies of interest as labels, and I run a predictive model. And in the end, what I get are outputs of all of these points with their likeliness of belonging to each class, or the probability of each point of belonging to each of the classes I'm looking for. So that's the first step of my algorithm. And this is what I get as an output, are just different rasters showing showing the probability for each points of belonging to my classes. So you see here, these are the different things. It's quite small because we're looking at pixels values for these mapping points. But what I can do now is run my WNet segmentation algorithm. So what I'm trying to do is segment my remote sensing data in a way that makes geological sense. So what I'll do is I'll use my MAG data here combined with my DEM, because in these neck of the wood, the DEM actually reflects the underlying geology. I'll use my control points that I generated from my large language model embedding. And through the VNet, what I get as an output are the probability map for each of these classes, each of the rock types that I'm interested in looking for. So if I go one step beyond that, I can now display my results as a map. So instead of saying this is where amphibolites are found, which is the typical way we were to do it, and again, if you look carefully, I only have control points here. Okay, so all of the rest of the amphibolite bodies have been extrapolated from geological interpretation. I can produce a heat map that says this is where you are most likely to find amphibolites, right? And this is what you're seeing. If you look at both products, there's some good sort of correspondence in the distribution of the amphibolites, but there are also some differences. And that's really interesting because basically now you have a product that's live. Running the whole thing takes about an hour. So you can update your geological map as you please, or even tailor your geological map towards what you're trying to find and towards a sort of lithological model you're trying to find. And that's really interesting in sort of how these things can be applied. So if we move to another example of these sort of segmentation using AI, this is an example that comes from Tasmania. It's a Balfour region, so it's just a little subset of the Tasmanian island there in Australia. And for that area, we had a lot of different inputs. So again, that's all public data, but we have a MAG survey, we have gravity grid, we have digital elevation model, and a radiometric grid as well. So from there, what we do is, again, we'll clean the data, we'll generate our input layers for the segmentation, and this is what we are left with. Then there's a series of training images that are constructed from image augmentation. So what we do is we break down the input survey into different tiles, and all of these tiles, we rotate them, we deform. We make them different by just different image augmentation techniques, and we can train our algorithm. So the algorithm is trained to predict the classes, and again, in the end, what we get is a prediction of each class being right. So we can stop there and just look at the probability map for each topology. But we could also use something like argmax, or the maximum probability for each class, and recreate our geological map. And this is what you're seeing here on the left. So the left is the automated map that was generated through the image segmentation process. And on the right is the real geology. So what you can see is there are some similarities in both maps. So you can see that sort of this rock body is also delineated here as part of the automated mapping, so that's interesting. What we're seeing here is there's this sort of a unit here that's just covered from the ocean, so it's all sort of a modern cover. So we do map this slightly more extensive area on the automated map. There's also on this map, you see there is a big data here, and we also see it here in the data. So there are similarities between the two products, but what we don't want to do is basically copy the geological map, because it already exists. You can train the algorithm to replicate the geology map, but that's not of interest because it's something that already exists. All right. Yeah, so that's it. I mean, that's an example of how we could use sort of AI and probabilistic models to generate new products for communicating geoscientific information. The other way we could use is to generate mineral system targeting maps. So basically trying to generate exploration targets through the use of AI. In that case here, what we're doing is we're combining vision image transformers and predictive and supervised learning to generate that predictive model for a mineral system. So traditionally, what's been done by the geoscientific community or by exploration geologists is we'll look at the data, overlay it in a GIS software, try to put some transparency, and then try to see what patterns we see in the data to try to explain the presence of mineralization. So we can train algorithms to do the same thing, but way more efficiently. The other thing is in terms of communication, what we're trying to move the industry away is those maps here you see where the exploration targets are drawn using PowerPoints with dotted circles, because these don't mean anything. For one thing, they don't have a shape that makes sense in terms of the geology. It's just a circle. The second thing is we don't understand how they came to be, right? Somebody just took a circle in PowerPoint and put a label to it that says target 2. But what is target 2? What is it made for? Where does it come from? What explains it? We have no idea. So besides the geologist telling you, well, trust me, this is a target because I know my shit, we need to move away from that, right? And again, that's not because I don't believe in geologists, but because I know how biased we are in the world, right? And there's if you look on the internet, there's tons and tons and tons of these different maps, right? So targets, some of are more complicated than other. And then if you've ever been sort of on the exploration side, trying to market your company and try to go towards financing for exploration, if you show these maps to bankers, I guarantee that within 2 minutes, they'll pull out their phones and start texting other people because they don't understand the data that's underneath them, right? So they're looking at a heat map or a mag. They don't know what the mag is. They don't even know what it represents. They don't know what the data is. It means nothing to these people, right? So we need to find other ways to communicate our geoscientific information. So what we're proposing on doing here, as part of our work, is how can we combine all of the geological information that exists for a property, for an area, or an area of interest, and produce a simplistic output that's going to be easy to understand to everyone. So we want to go from all of these data that are technical and only make sense to the geoscientific community to a product that says, well, this is a drilling target, or this is an exploration target. How can we do that? Our proposition is to use our combination of transformer for data embedding and supervised learning to generate these targets. So what we do, the first thing is we'll compile all of the data. So you can create what's called a data stack. So that's all of the existing data for the property. So that could be, again, numerous types of data, but it could be the DEM, geophysics, satellite imagery, lithology, faults, map points, geochem, anything you want, anything that exists. And then from examples of mineralization, we create our learning labels. So the labels are binary, meaning we're looking for positive or negative examples. Positive examples is somewhere there is a mineralization of interest. Negative is somewhere you look for and there's no mineralization. And the negative is really important, right? I want to work with true negatives in training my algorithm. I can't say that the positives are areas where it's mineralized and the negatives are everywhere else. That's not a good way to go about it. I want to use true negatives, and these true negatives have to be areas that have been explored without any success, right? So in that case, you could use drill holes, you could be using historical mines, you could be using rock sample from surfaces, rock chips, whatever you want, as long as it makes sense. We run that through a predictive modeling exercise. And what we output for this types of maps are the probability of finding mineralization, the elevation of that mineralization, so where it sits in the Z value, and the variance, because we use a stochastic approach to generate these models, so we can produce a variance of how, and then produce a risk map of our exploration targets as well. So the overall process looks a bit like that. So the first step is to gather the data stack and the training examples. Again, the training examples here are made from the drill holes. We pass those and we rasterize those two things, create a bunch of rasters, and run that through a vision transformer architecture for data embedding. Just got scared. So we run that through a vision transformer, and we embed all of that into a latent data space. From that latent data space, we also reuse our learning examples and use a supervised random forest classification algorithm to make a prediction for likeliness of finding mineralization. What's interesting in that case is since you're using supervised learning and you're doing your machine learning correctly, you can get all of the performance metrics for your model. So you know how well and how accurate your model is, and that's really interesting, and that it can be used to explain. And you can also get that thing here that's called a feature importance map. And I'll show you an example later on, but that's really, really interesting in terms of creating those mineral system maps. So if we move to our example, we developed the first pass of that using a public data set for Flin Flon in Manitoba. It's a DMS system. So you're seeing here is the satellite image for this area. So you see that it's an historical producing area. You clearly see the footprint of the mine there. But we have all of the geophysics prior to that exploitation, and we also have the full drilling database. So what I did, obviously, is I removed all of the drill holes that were intersecting the actual massive sulfide lenses. And my goal was to see, can I use the geophysics data and a machine learning algorithm to predict where these massive sulfide lenses would be. So this is what we set out to do using this technique. So this is the data stack for the area. So we have airborne mag, we have airborne gravity, and ground mag. and all of the different derivative product. I'm actually inputting all of the airborne gravity was a gradient survey, so we have the gradient in different axes as input. The mag is also it's just a ground mag, normal ground mag, but we also have the derivative of these product, and we create different layers of information. So this is the data stack. So right off the bat, you see that trying to see a statistical correlation for each of those pixels in the surveys in regards to predicting the mineralization would be pretty hard to do manually because there's a lot of data. Then we have the drill hole database, and these are all of the drill holes that we kept that didn't intersect any of the true mineralized bodies, and we're trying to see if we could use them to make a prediction. So what we go, how we set it about is that we took the drill holes, and all of the intervals that didn't have any zinc or copper in them are classified as negatives for our training purposes, and all of the areas that have, or all of the intervals that have zinc and copper are classified as positive. So we create a binary class for our sort of two-class prediction model here. And then the way we train the model is through spatial iteration. So one thing we'll do is we'll train a model using this data set, and this data set, and this data set, and test on the remainder. Okay, so that's the first pass. Then what we'll do is we'll train using these areas and test on the remaining. And we do that over and over through a number of iterations. And the goal is to have a geographic spatial representation in our testing and training data to make sure that we're capturing sort of the different domains in the data. So through the data stack and the drill hole, we produce the heat map. Just as an intermediate step, this is the embedded data space. So when we run that through the transformers, what we output and what we use as input for the supervised random forest are these rasters here. And these rasters are the embedded data space. So they don't mean anything. So you can't say that one of these rasters is the mag or one of these rasters is the gravity. It's just the embedded latent space of the data. So it's a representation of the data in 24 dimensions that we can't really comprehend, but it actually makes a lot of sense in terms of making a prediction, and you'll see later on. So once we run the predictive model, this is what we output. We output a heat map or a probability map to finding positive examples or finding mineralization. This is what you're seeing here. So you see that there's a few areas of interest that could be considered exploration target. Since we have drills, we also know at which depth these intercepts are, these positive examples are. So we can also make a prediction of how deep all of these positive examples should be. And this is what we're getting here. So from that 2D grid embedded space, we can make a prediction in 3D. And that's really interesting. Now you're starting to see where you should go and explore next. So you have different targets. They're easier to understand now. If you show that to someone and say, well, the pink represents high likeliness of finding mineralization, people will understand that, right? If you were to look at it as a geo, you already see trends in the data. You can see how it represents the space, and that's really interesting. The other thing that's outputted as part of the results is the SHAP value map, or the feature importance for prediction. And that is really interesting. We produce one for every target or every sort of cluster of positive examples we have. And this becomes a really interesting tool. And the first people we've shown that to were really interested, and it sparked discussion almost immediately. Because what you're seeing is how important, what is the most important predictor for your mineralization. In that case, you're looking at airborne gravity gradient on the YZ axis. And if you're looking for a massive sulfide deposit, that makes sense because you're looking for a dense body in rocks that are less dense. So a gravity gradient would make sense as a predictor for a massive sulfide lens. So you have two of the airborne grav product as being the main predictors. The third one would be the airborne mag. And again, we know there is a mag relationship, so you're looking at different values. And then you can see, well, it's interesting because on the YZ axis, I'm looking for a high gravity gradient, whereas for just the Z axis on itself, I'm looking for low gravity gradient. So you can start to understand how this target came to be, how the decision is made. What we're lacking here, and that's something we'll add, is another box that says that the testing accuracy of the model is something like 93%, right? So you have a measure of how accurate your model is in making the predictions on known areas. You know what came into making the prediction. So you start to generate a product that has some more explainability. But if you remember those dotted circles that were drawn in PowerPoint, we're way beyond that now, because you now have something that has a shape and some explanation. And here what I'm showing is the real sulfide lenses. So again, they weren't used as part of the training. The goal was to see, can we predict the location of these massive sulfide lenses in 3D? And if you were to look at it, there's a pretty good correlation spatially between our high prospective areas and those massive sulfide lenses. So I was really, really pleased with those results. I mean, there's a good proof of concept there that there's something to be done there. So obviously, that's just to show that like the drill holes we used didn't really intersect the massive sulfide lenses, but we were still able to predict them. And the last thing I wanted to show, and that was really interesting to me through the different iteration I made, is I got the results and they were displayed exactly on that fashion. And what I saw really quickly is there is a break in the predictive model around here. And funny enough, if you look at the Flin-Flon model, there is a fault running right there. So you see that the predictions stop at the fault. The other thing you're seeing is the prospective horizon for the VMS has this shape, which is a folded area. So again, it's our key in VMSs, it's tightly folded. So you see the fold there, and then you see the fold sort of pick back up there. So if you look at it in 3D, it starts to make a lot of geological sense. And that was a really good surprise to me because none of the geological objects were used as input. The only inputs are the geophysics product we had for the area. So the model actually starts to catch up on how these things sort of behave. And then, yeah, you can see the VMS horizon again. You have one area there, another area there. So there is some good relative spatial correlation with the prediction, even if none of the geological objects are being used. So we're really, really pleased with that. Another area where we did the same thing was for fine sort of high-grade gold in vein. So that's in Australia, Victoria province. So it's orogenic gold prediction. And again, we use the drill holes as training examples. In that case, our training examples are everything above 15 grams per ton. So it's high grade, really high grade. That's our positive examples. The remainder of the drill hole trace is used as a negative example. And this is the data stack we had there. So a lot more data. You have brown IP, you have brown mag, regional mag, radiometrics, distance of faults, the distance, different fault family, geochem data, soil geochem, so a lot of data. So again, trying to see the correlation across all of these data set by eye for a human, impossible. Okay, so we might be able to catch more sort of correlation in there. And this is the prediction for the mineralization in 2D. So that's sort of the heat map that was produced out of all of those rasters. And again, when we push it in 3D, this is what it looks like. And that was really, really interesting again to us because we're getting bodies that actually make sense. You're seeing each of the targets also come with their own labels, so we can explain each of the targets in regard of the predictive modeling. So if I zoom in first, obviously we found the two main deposits, which are known because they've been drilled out, but there's a good spatial correlation between the known prediction. So our model captures that well. But again, a little area sort of stands out right outside of the drilled out area. And this is sort of this cluster of high prospective points here. So it's sitting just outside of the drill hole area. We're kind of interesting when we show the results to the clients. It's like, well, speaking of which, we have some drill holes that are pending results, and this is where we drilled them. So now we're sort of impatiently waiting for the client to release the assay results for these intervals, because that would be a good proof of concept. If there was any gold or veins there, it means that the model actually picked up on the structure, the mineralized structure. Another area that stood out was just located south of the main ore body. So that's the little area you're seeing here. Okay. And when we show that to the client, we put on the map for the mafic dike that controls the mineralization, and there was the presence of that mafic dike. Furthermore, what was really striking to me is you're seeing the kink there in the shape of the target, and it's really reminiscent of the same kink we're seeing here. So that's called structural repetition. There's actually is this fault running along here. There's another fault running along there. And again, it's sort of to make geological sense. So from no geology and formation per se, we're able to sort of see sort of geometric correlation appearing in the data. Lastly, there's a really, really strong area here in terms of our predictive model. It was really interesting. It's really wide because it's not constrained by as much data as the rest, so it's outside of the ground mag and IP data coverage, so it produces just a bigger anomaly in terms of predictive. And then when we showed that to the clients, they were like, oh, interesting enough, there's a historical mine there. We don't have any of the drill holes, but we know there's workings there. So we found a mine that we didn't know was there when we got the data, but they knew about it. But and then they looked at the data set and they said, well, interesting. So in the rock data, we're looking for so the mineralization is linked to areas with low nickel. So that was interesting to them, and then they're like, oh, cool, so we're looking for other, so here the dip direction of the bedding, we're looking for high azimuth value, so basically bedding that's more or less north-south, so that was interesting as well. So you can start to explain your targets and relate them to your mineral system analysis, and the goal there is to have these targets being explainable to geoscientific people, and to use the SHAT values as sort of a tie-in to your mineral system analysis or your knowledge of how these deposits are formed. So yeah, I mean, yeah, so these are the two main examples I wanted to show you of how we can move from sort of deterministic approaches that says this is this, that's 100% sure, to more probabilistic approaches in the geosciences. And I think that has to do with the use of artificial intelligence for a few reasons. One, AI produces probabilistic output by default, so it's really useful. It's quite useful to just use the output as geoscientific products. Because also you can enrich your input data. So if you use probability of lithologies instead of just a pure lithology as input to your model, it's a lot more powerful in terms of predictability. You'll be able to leverage a lot of information that's sort of considered stuck in your databases, like text, like descriptions. And it's a way to simplify complex information to better educate the public or to have the public understand what you're trying to get across in terms of messaging. So that's about it. I'm 1 hour on the dot, so rarely am I on time. So we'll take it as a good thing. If you have any questions, please go ahead. I mean, yeah.
Yeah, Billy, thank you so much. Questions? I have actually 2 questions. Well, good. I don't know, can you see me here? Yeah, great. Vinicius here. I have 2 questions. The first is more technical. The other one goes more to the side of the communication you brought up. The first one is on the fling-flong case you presented. And it's about use basically magnetic field and gravity data, right?
Yeah.
How well the model behaved with the depth? How well the model fitted with the observed depths of the mineralization or what you found there? That's because I'm asking because mag and gravity are not known for a good depth estimation and more lateral. How good was it?
Yeah, what's interesting actually is since we're using the embedded data space to make the prediction and we're using computer vision to make that data space, we started to see it pick up on wavelength features in the data. So if you think of mag and gravity, all of the potential field, the wavelength is actually a function of the depth of the anomaly or of the object. So if the embedded data space we're using to make the prediction picks up on those wavelengths and sort of separate them, then it's like you're using an inversion. So every sort of embedded data space has sort of a depth profile to it. So that's why I think we're seeing such a great correlation in sort of depth prediction and the prediction of the anomalies and the VMS, just because the embedded space does way better at representing the different wavelength than just using the raw input. If you were to use random forest, you're just using cell by cell, so you're not even accounting for textures or different wavelength anomalies. So I think that's what is the powerful, so the enhanced power of the predictor here. But again, it's hard to really understand because the embedded space, like unless you look at them, it doesn't make sense. We did another one for porphyry copper, and one of the layers in the embedded space, when we looked at it, it highlighted the underlying intrusion really, really well. So the big backlit that was sort of underlying the area was sort of depicted in that one of these layers in the embedded space. So we start to see the transformer actually pick up on features that make geological sense. Again, trying to explain that is tough because we don't know how this embedded data space comes to be. The way we train I didn't touch on that, but the way we train the vision transformer to make the prediction is through a classification. So basically, when we go to this step here, what we ask the transformer is to classify the little images. So we'll patch all of the input rasters, we'll patch them into a multi-channel input, and we try to classify each patch as being positive or negative, depending on how many positive examples there are on the patches. So it's a classification problem that the transformer is trying to solve, and a reconstruction of the input images as well. So it's sort of twofold. And then, yeah, we just use the latent space to make the predictor as an input for predictor. So I think it picks up on the wavelengths and textures that are important to represent the depth of the objects.
Yeah, thank you. A follow-up question about that. Flame foam is actually well-behaved in magnetic field. Have you ever tried something like that in an area of interfering anomalies and magnetic anomalies? And we're repeating a question I did to Erwan earlier with considerable remnant magnetization. They're interfering in the map.
Yeah. No, so we currently have 5 partners in sort of developing the technology, and none of them has any of those issues. So we're working. One of our partners is a lithium pegmatite in northern Quebec, so no really remnant problem there. There's no iron formation in the area, so we don't see any of that. The other one is a porphyry example in British Columbia. Again, no remnant bodies there. The other one is Southern Cross, which is the gold example I showed you. And the other one is silver veins in Mexico. So none of them have that issue. I'd be curious to see how it behaves, because that's a good question. But we've yet to encounter a project that has that. Yeah.
If you ever want to play with something like that, just come to Brazil. We have plenty.
Oh yeah. I'm sure that the Carajás basin would be interesting to work in just because of that. Sure.
That's great. So going to my second question, it goes straight to what you said about the latent space. And how do you see in the communication phase, especially when we talk about ESG, for example, for the transparency that's needed in the government icon of the ESG, how we explain for an example, stakeholders, what we are doing that, and how do you see not only the latent space, but artificial intelligence, how do you see that we as geologists, geophysicists, specialists in AI, explaining that kind of thing, put in the paper, put it on the reports, and explaining for people that are out from our fields, but still they will be the stakeholders. They will pay for our research.
Yeah, it's a good question, and there's no obvious answer. I don't think there's a silver bullet there. One of the way to do it, I think, goes through educating the public. The more we understand AI, the more we'll understand how they function and what comes into it, and sort of opening the black box of AI. Because if I remember 8 years ago when I started doing AI, people were like, oh, I don't trust it, it's a black box, it makes a decision, I don't know why and how. I've been, ever since giving courses at PDAC, Roundup, all over, just trying to explain the black box and how it works. And more what I see is I sometimes get on call with really doubtful geoscientific people or older geologists. I'm like, I don't believe in AI. And by the end of the hour, they're actually converted because they've understood how it makes the decision. And they can actually know that they can evaluate it and sort of test it as well. So there's performance metrics, the chat values, the feature importance, that comes to play into sort of making people understand it. But if you go not so long ago, if you talk about just a geophysics inversion, just a mag inversion, most geologists, they know it exists, but how it functions is a mystery to them. They think it's just a matter of selecting a button, it just pushes everything in 2D, 3D, and then you have an inversion. So it's the same thing, right? It's sort of, when you don't understand it, it's hard to comprehend, but I think while people sort of get more and more educated, it's going to be easier to explain. And I think it has to be as transparent as possible. And that's one of the key things when I joined Verify is I wanted to make sure that the company was willing to explain their processes and the processes that we use to generate these things, because otherwise I don't think there's value in it. There's a lot of other consulting outfits that say they do AI to make predictive maps or whatever, but they never explain how it's done. And for me, that's an issue, because you're sort of preserving the black box. It would be equivalent to say, well, I did a mag inversion, but you're not saying if you're using UBC, VPMG, SIMPEG, it's just, I did an inversion of the data. You don't know what algorithm's being used, and it has no value, right? So it comes with education and being transparent in how it's done as well.
We have one more question here. And
yeah, no worries.
Just to let you know, I know exactly how you feel about the magnetic inversion. Like most of my career, I was doing that with UBC and then model vision.
Yeah.
Jean-Philippe, Glaucio Bucherato speaking. We've met a few years ago at PDAC. I'm originally geologist. I've recently finished my PhD at mine engineer in Escola Politécnica at USP again as well. And I'm discussing, actually I have two questions. One complementing Vinicius' question about the good practice about related to artificial intelligence for reporting proposals. As you know, more than I, CIM has great material to help the geologists to report properly for exploration proposals and mineral research proposals as well. But we still don't have good practice recommended for AI proposals. First question, I would like to know if you participate in those groups in Canada. And I was at the Verify booth at PDAC this year. It was a really great place to discuss innovation. And I'm not sure if it's today, the day, but probably other time. But I think the platform that you are developing will be probably the best one that work to show the innovation, all the layers of information to the industry. And my focus is straight to the quality of the data. So I do the hard work to give you to do the magic. So I would like to know how your work is going to the platform. If you can tell us today or other day. And invite you, if I can, invite you to tomorrow morning at 11 our time. I will show some part of our work, that the methodology that we developed here. And we are doing a partnership and trying to do the partnership with the university as well.
Okay. Yeah. For your first question, it's actually funny because there is currently a PDAC initiative around reporting AI, or general AI. So, there's exploration guidelines for the industry that are made by the PDAC. They're just guidelines on how to go about the drilling, geochem, and all of this. So that's something that's happening. So there is a group that has started with the same intention, but towards the AI. It's not as straightforward because it's a really broad subject, and capturing what's important and what's not is tough, but I think it's in the works. I don't know if the CIM has guidelines as well. I think if PAC puts out these guidelines, they'll probably join the thing, but it's mostly the Canadian initiative. In terms of proper reporting format, like NI 4311 or JORC, I don't see it being, so they probably won't catch up because it mostly pertains to resources. So yeah, it's interesting to see where it's going to go, but I think, again, educating the public is key here before all of those guidelines exist. In terms of verify, and again, I didn't want to be too sales pitchy here. The goal was just to present how AI can be used. The platform you saw for the presentation was made by Verify, so we used to make our presentation. One thing I didn't mention is we have for objective to build a web app for people to be able to run the predictive models themselves. So what we want to do is move away from the consulting service industry, where if you want to run an AI project, you have to hire consultants. They'll do the work for you, but then you get the results and it sort of die there. We want to generate a user interface for people to be able to run their own predictive models. So we'll start with the targeting initiative that we announced. So that's going to be a UI where you have your layers of information, you have some model parameters you can play, and you'll be able to generate your predictions. And the goal, again, is just to give the tool to the public for them to use and learn. And you can't break it, right? So it's just a question of using it. The decision, you can also, we'll have some documentation how parametering the different hyperparameters for the algorithm works. But otherwise, we want to put that in the hands of the public to make sure that people start using it on the daily basis. And yeah, if you want to invite me for tomorrow, just send me a quick email. For
yes, please.
Oh, yeah.
Thank you. Thank you.
One more question here.
Yeah.
Bye. Bye.
Hi, Manuel's here. Nice. Thank you very much for all the learnings for today, development. Considering that some geologists will still doing and will keep doing geological points, and how we can make some patterns to be more machine friendly in terms of describing the outcrops. It was very interesting your approach, considering that people in the past described it looking for some metals or for some commodities.
Yeah.
In the future, we use that for another proposal. So how we can develop standards in order to make the future geological field more useful for the machine use?
Yeah, I think that's, again, twofold. I think the verbal descriptions of the rocks are already pretty good. They're way better than the actual names we give to rocks. So if I tell you about sort of a medium grain crystalline rock that has quartz, feldspar, biotite, you know what I'm talking about, right? So these are sort of typical, that's common, or so that's pretty much standard across the whole geological sphere. So that's, I think that needs to keep going as unstructured text, because now we have ways to extract that information that's automated. The other part to make it more useful, I think it goes to multi-parameter data acquisition. So capturing mag susceptibility, density, hyperspectral, any types of sensors, basically we could sort of carry in the field, have your XRF and have the geocam. All of that for every point or every rock will become really interesting. So capturing multi-sensored information, logging into a database that has relational capabilities, not Excel. That's the other way to do it. We need to have better databases and better way to store all of that data and organize it so it's ready to be used for AI. And because right now, if you were to run an AI project or try to solve something using AI, I would say that 70 to 85% of your time is going to be spent preparing the data, right? So you're losing a lot of time for data preparation, formatting, cleaning up. So we need just to make sure that the data is well taken care of, so it's easier to get into the pipeline for AI sort of specific applications.
Any more questions? One more, right?
Hello, hello again, and thank you for the presentation, and congratulations on the algorithm. I thought it was really impressive. And I was thinking about the first algorithm. It's interesting to see the way that it, at least from my perspective, it could also be applied in thin section analysis, because when you do a description of the thin section, you basically just describe everything, and then you come up with a name. Do you think that your algorithm, it could be used like what you produced here? It could also be used in this this so-called digital petrography. And another question is that you say that maps are deterministic, and that when you would your algorithms, they're mostly probabilistic, and you showed like several different maps showing different types of rocks which could be expected in the region. Do you think it is possible to create some sort of map which has like the probability for every rock in that area, or do you think like geological maps in that aspect are like inherently deterministic? Thank you.
Yeah, I mean, in terms of the thin sections, I think, yeah, segmentation of images is built for that. I think it'd be really easy to do a classification problem using thin section images, just through either refracted light or reflected light. That's if you have a digital image of the thin section, I think that would work pretty well. The second part is, I'm not quite sure I understand, but yeah, I mean, it's possible to generate a map of, you could basically, instead of feeding in your desired rock codes or the topologies you're looking for, you could use all of the available ones for the region and have a probability for each one on the grid. Yeah, that's totally possible as well. So instead of, yeah, but what I want to make sure is that instead of representing the maps like we used to, we have some sort of probability underlying it, so we can know how likely and what is the risk and interpretational risk of our maps behind them. Because, I mean, what we see on those geological maps, or I'll try to just find my slide again. Yeah. So if you were to look at this map, there's a lot of like misclassification areas, and the map doesn't tell it. So if you don't put the points underneath, all these points are classified as sedimentary rocks in terms of the mapping point, but the map has them as an intrusive unit. So there is an uncertainty about the interpretation there. There's a risk associated to that interpretation, and it's not captured when you just look at the map. So I want to make sure that the industry sort of understands that, and we have ways of quantifying it now.
Thank you. Thank you.
Yeah. Any last question? Okay. Just finished.
Thanks for the presentation. I was thinking, when you stack those features, correct me if I'm wrong, every feature must have the same shape and pixel size, right? Or no?
No, actually, the only thing that's important is that they have the same corners, so they have to be clipped on the same area of interest. The size of the pixel doesn't really matter, so the resolution of the survey doesn't matter. We just resample it to the same pixel size afterwards. When you input data, it doesn't really matter. In terms of the shape, you can work with data that are not continuous across a grid. So, like again, if you go to, sorry, I'll just pull out an example. If you look at the data stack we had for Southern Cross here, you see that the mag, which is the ground mag here, has some null values in it. It doesn't cover the full grid, but the prediction also works on the full grid. So you don't have to have the exact same coverage of the data, which makes it interesting as well compared to if you were to use random forest, you wouldn't have any prediction for that area because there's a no data value in the system, and it just doesn't make a prediction when there's a no data value.
My question was about pre-processing, so you don't need pre-processing too.
No.
Yeah. Thank you.
Yeah.
Okay, Jean-Philippe, we're finishing here. I'd like to thank you very, very much for being part of our workshop here. And that's it. Thank you very much. It is the end of the first day.
Yeah, thank you for inviting me. If you have any other questions, let me know.